One day, the solar system may face a threat we can't outrun, not an asteroid, but the galaxy itself. And when evacuation isn't enough, there's only one unthinkable plan left: turn the sun into an engine and every planet into a passenger. Could a civilization really steer a star with a Shkadov Thruster? And if someone already is, would their moving sun leave a fingerprint in the sky? The sun is not merely a light in our sky, it is a mass in motion, and motion can be rewritten. Somewhere between physics and audacity lies a method to make that rewriting permanent. This film follows a single idea as it grows from a clever asymmetry into an architecture of fate, the Shkadov Thruster. A mirror on a colossal curve, poised near a star, turning sunlight into a steady bias, small in force, vast in consequence. But an idea this large does not remain gentle for long. Once you accept that stars can be persuaded, the next question arrives with an edge. How hard can you push, and how fast must you decide? The question is not whether the universe permits stellar engines in principle. The question is whether the costs, risks, and signatures make them realistic, and whether the sky has been quietly keeping their records. Because if a civilization ever learned to pilot its own sun, it would not just change its future, it would change what home means, turning an origin into a vehicle and destiny into a plotted course. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. From galactic hazards and chaotic dynamics, we descend into the Shkadov Thruster's quiet thrust, then climb toward harsher engines, brutal construction, and the economies that feed them. Finally, we return to the night sky, searching for the thermodynamic and kinematic traces such journeys cannot erase. We like to imagine the solar system as a finished machine, stable, predictable, and safely isolated. That picture is comforting, and it is wrong in ways that matter. Our home is a dynamical system, and dynamical systems can drift, amplify noise, and surprise you. In a planetarium it looks orderly, clean ellipses, calm clocks, a cosmic diagram that never changes. In reality, the diagram is a snapshot taken mid-motion, while forces continue to accumulate in the background. The unsettling premise is simple. The solar system is not a sanctuary. It is a moving target inside a violent galaxy. Gravity looks deterministic, yet long-term prediction breaks down in practice. The reason is not ignorance of physics or missing equations hidden in some future textbook. The reason is chaos in the n-body problem, where many bodies tug at once. Every planet perturbs every other planet, and those perturbations never fully cancel. Even when the average pull seems to balance, the timing does not, and timing is where the future hides. Over time, tiny differences in position and velocity grow into different futures. For the inner planets, numerical integrations show a horizon for precise certainty. Beyond roughly 60 to 70 million years, trajectories diverge in ways that cannot be reversed. The system remains lawful, but it becomes unpredictable in detail, because nearby solutions separate exponentially. A millimeter today can become a million kilometers later. That is what chaos means in celestial mechanics. Determinism without long-term foresight. If you could hover above the solar system, the change would be almost invisible at first. Two nearly identical simulations would track each other like twin shadows, then slowly slip out of phase. The divergence is not a single dramatic jump. It is a quiet widening, orbit by orbit, as small errors are stretched by repeated gravitational encounters. The mathematics calls it sensitivity to initial conditions, but the plain language version is simpler. The future depends on details we cannot measure perfectly. The mechanism is not magic. It is resonance, feedback, and slow pumping of orbital elements. A small periodic shove can add up if it matches a natural frequency. Eccentricities can rise, inclinations can tilt, and precession rates can lock together. Precession is the slow rotation of an orbit's orientation, like the wobble of a spinning top. When resonances overlap, stability islands shrink, and the phase space becomes a maze. In that maze, outcomes that seem impossible become merely improbable. Mercury's eccentricity can be driven upward over billions of years in some solutions. Mercury is small, close to the Sun, and constantly jostled by the gravitational rhythms of Venus and Jupiter. In a fraction of simulated futures, its orbit becomes more elongated, bringing it into destabilizing proximity with its neighbors. That can cascade into orbital crossing risks for the inner planets. Even without collisions, altered eccentricities change climate forcing and impact probabilities. A more eccentric orbit changes the seasonal distribution of sunlight, and it shifts how a planet exchanges angular momentum with the rest of the system. On Earth, subtle orbital cycles already pace ice ages over tens of thousands of years. If those cycles were amplified, the familiar boundaries of habitability could narrow. The solar system does not need to fall apart to become hostile. This is the first stake. Even in perfect isolation, long-term orbital certainty is limited, and the limit is fundamental rather than technological. The solar system is a clock with gears that slowly slip. It still tells time, but not the time you hoped for. The deeper lesson is psychological as much as scientific. Stability is not the default state of a many-body system. Stability is something that must be demonstrated again and again across time. But isolation is the second illusion, and it fails even faster. The solar system is embedded in the Milky Way's gravitational field. The galaxy supplies tides, encounters, and shocks that add new perturbations. When you zoom out, the Sun is not the center of the story. It is one mass among hundreds of billions, moving through a structured environment with spiral arms, clouds, and stellar streams. The Sun orbits the galactic center while drifting through a sea of stars, gas, and dust. Stellar density is not uniform, and neither is risk. Relative velocities set encounter timescales and impulse strengths. A slow encounter gives gravity more time to work, while a fast one delivers a sharper kick. The Sun's kinematics decide what we pass near, how often, and how hard we get kicked. On million to billion year timescales, close stellar flybys are not rare. A passing star does not need to touch a planet to matter. It only needs to pass close enough to tug on the outer solar system. The outer regions are loosely bound, and they respond like a shaken cloud. The inner planets sit deep in the Sun's gravity well, but the outermost bodies live near the edge of escape. Far beyond Neptune lies the Oort cloud, a vast reservoir of icy bodies. It is not a neat ring. It is a weakly held swarm extending tens of thousands of astronomical units, perhaps even approaching a light year in its farthest reaches. Its members orbit slowly, taking millions of years to complete a single loop. Their binding energy to the Sun is tiny, meaning a gentle nudge can rewrite an orbit. The Oort cloud is also a historical artifact. It is thought to be built from leftovers of planet formation, scattered outward by the giant planets early in solar system history. Some fragments were flung onto wide, fragile orbits and then parked there by galactic tides. In that sense, the cloud is a fossil record of ancient chaos. It is also a reservoir of future surprises. The Milky Way exerts a tidal field that slowly torques those distant orbits. The tide is weak, but it is persistent, and persistence matters over long durations. Molecular clouds add stronger, localized gravitational disturbances when we pass near them. Passing stars deliver impulsive kicks that can change perihelia and inclinations. Each effect is small per object, yet enormous in aggregate. When the Oort cloud is perturbed, some comets are nudged inward. Their long periods mean they arrive with little warning on human timescales. A small change far out can become a deep plunge toward the inner planets. The geometry is cruelly efficient. Shift the perihelion slightly, and a frozen body becomes a solar grazing projectile. The result can be a comet shower, a temporary spike in impact rates. Visually, the process is almost elegant. In the darkness beyond Pluto, a faint point of ice is lifted by a passing tide, then falls inward for millions of years. It accelerates silently, growing a coma only when sunlight finally reaches it. By the time it becomes visible to telescopes, much of its trajectory is already decided. The warning is late because the journey is long. Impacts are not just a crater problem. Large impacts can trigger climate collapse fires and ocean chemistry disruption. Dust and sulfate aerosols can dim sunlight, while re-entering ejecta can heat the atmosphere enough to ignite forests. Even smaller impacts can reshape ecosystems if they cluster in time. The Oort cloud is a loaded dice cup, and the galaxy shakes it. We cannot assume the next shake is far away. One encounter is already on the calendar. Gliese 710 is a modest star, but its trajectory is unusually close. Current measurements predict a close pass in about 1.3 million years. In astronomical terms, close can mean a fraction of a light year. That is still tens of thousands of astronomical units, a distance that dwarfs the planetary orbits. The prediction is possible because modern astrometry measures stellar positions and motions with exquisite precision. Missions like Gaia turn the sky into a dynamic map, where stars have velocities and future paths rather than fixed constellations. Even so, uncertainties remain, and the exact minimum distance can shift as data improves. The important point is not the exact number. The important point is that close passes are real, calculable, and recurrent. Gliese 710 will not enter the planetary region, and it will not graze Neptune. Its influence is expected to be felt primarily in the far outer solar system. That is enough. A flyby at that distance can reshape the distribution of Oort cloud orbits. It can increase the rate of long-period comets entering the inner system. The effect is probabilistic, like changing the odds rather than aiming a single bullet. This is how hazards arrive. They do not announce themselves with a collision course to Earth. They arrive as statistical pressure, as a raised background of inbound objects. The planets keep circling, and the sky slowly becomes more crowded with threats. The danger is indirect, delayed, and hard to attribute. If a comet strikes long after the flyby, the cause can be invisible to memory. Stellar encounters are only one category of galactic hazard. Another is radiation catastrophe from nearby stellar death. Supernovae are rare near any given star, but the consequences are outsized. A sufficiently close supernova can sterilize surfaces and collapse ecosystems. Distance is the difference between spectacle and extinction. The same explosion can be a beautiful nebula from afar, or a biological crisis up close. Massive stars like Betelgeuse remind us that explosions are part of the neighborhood. Betelgeuse is not close enough to guarantee disaster, but it illustrates the scale. A core collapse supernova releases intense light, neutrinos and high-energy particles. The immediate flash can be bright, even in daylight. The longer tail can be lethal, because the galaxy does not stop delivering energy after the first moment. Historically, humans have watched supernovae without understanding what they were. Ancient observers recorded guest stars that appeared and faded, leaving behind remnants we now image in radio and X-rays. Those records are reminders that stellar death is not theoretical. It has happened within our galaxy in the span of civilization, and it will happen again on timescales that do not care about us. Type Ia supernovae add a different risk profile. A white dwarf in a binary can accumulate mass and detonate, producing a remarkably bright and energetic event. IK Pegasi is often cited as a potential future type YA progenitor, though timescales are uncertain. The point is not a specific countdown. The point is that some nearby systems can become bombs, and we may not recognize them as such until late. What does close enough mean for a supernova hazard? It depends on the spectrum and the planet's shielding. A supernova within tens of light years can be dangerous. Within roughly 30 light years, the risk of severe biospheric damage rises sharply. Within about 10 light years, surface sterilization becomes plausible. Those numbers are not magic thresholds, but they frame the scale of vulnerability. The kill mechanisms are multiple and compounding. A gamma and X-ray pulse can ionize the upper atmosphere. That can drive ozone depletion and expose the surface to ultraviolet. Cosmic rays can rise for thousands of years, enhancing atmospheric chemistry changes and cloud microphysics. Nitrates can spike, and food webs can destabilize. The planet may look intact from space, yet its protective layers can be chemically dismantled. Ozone loss is not a single bad year. It can be a window where DNA damage rates soar and ecosystems unravel. Marine plankton, the base of many food chains, are vulnerable to UV. Terrestrial plants can be stressed, and climate feedbacks can amplify the shock. The biosphere can survive some hits, but not all. The question is not whether life persists somewhere. The question is how much complexity is erased. These hazards interact with the earlier chaos story. Orbital variations can alter climate resilience and extinction thresholds. A planet already near a tipping point can be pushed over by a smaller external shock. A stable orbit does not guarantee safety, and an unstable orbit can magnify any disaster. Risk is layered, not isolated. Internal dynamics set the stage, and the galaxy supplies the interruptions. So the question becomes strategic rather than purely scientific. How do you defend a civilization against threats that arrive from outside the planetary system? One approach is local defense. You can build telescopes, track comets, and attempt deflection. You can harden infrastructure, bury habitats, and store genetic archives. You can treat survival as an engineering problem, measured in warning time and impact energy. Local defense has limits. Deflection works best with warning, and long-period comets can appear late. Their approach vectors are steep, their speeds are high, and their compositions can be fragile and unpredictable. Shielding helps against radiation, but it cannot preserve open ecosystems easily. Underground survival can protect a remnant, but it is not continuity for a living planet. A civilization may endure while a world dies. The other approach is evasion at the system level. If hazards are tied to where you travel in the galaxy, then motion becomes a control knob. Reduce the rate of close encounters by changing your path. Increase your distance from future supernova neighborhoods by leaving them behind. Treat the sun's trajectory as a design parameter, the way sailors treat currents and storms. This is where stellar kinematics becomes more than astronomy. The sun moves through the galaxy at tens of kilometers per second relative to local stars. That motion sets encounter rates with passing stars and clouds. In denser regions, hazards rise. In quieter regions, hazards fall. Kinematics is risk management written in velocity. The same solar system can be safe in one corridor of the Milky Way and threatened in another. But planets cannot easily change their galactic orbit on their own. Rockets can move people, not solar systems. Generation ships can flee, but they abandon the sun's energy and the stability of familiar orbits. They also trade one unknown environment for another, carrying biology into a vacuum of uncertainties. The deepest lifeboat we have is the sun's gravity well. It carries the planets, the comets, and the long-term resources. If the sun could be moved, everything bound to it would come along. The planets would remain passengers in a shared gravitational frame. The Kuiper belt and the Oort cloud would still exist, but their future perturbations would depend on a new galactic route. The hazard map would change because our track through the galaxy changed. The idea is audacious, yet it follows directly from the physics we already trust. That idea sounds like myth until you remember what starlight is. Photons carry momentum, and momentum can push. Radiation pressure is small, but it is real, and it acts continuously as long as the star shines. If you can redirect a star's radiation asymmetrically, you can create thrust. If you can build structures large enough to survive near a star, you can turn luminosity into propulsion. The star becomes an engine, quiet, relentless, and patient. The concept is not about sprinting away from danger. It's about slow, continuous acceleration over millions of years. A small thrust applied steadily can produce a large displacement over geological timescales that can shift the sun's path relative to hazardous regions. It can turn inevitable encounters into avoidable near misses. It can also buy time, and time is the currency of survival. This is the cosmological imperative. Chaos limits prediction, and the galaxy supplies perturbations and catastrophes. The combined message is that safety is not a static condition. It is an active project measured in trajectories and timescales. If the environment changes on million-year clocks, then the defense must also think in million-year clocks. The ultimate defense may be to steer the entire system, not just shield one planet. Now the central question comes into focus. Can a civilization realistically build a stellar engine and pilot its star? Could we detect the signature of others already doing it? If such projects exist, they would be the archaeology of advanced intent, visible not as monuments, but as altered motion. The first step is to understand the simplest proposed design. We start with a mirror that does not orbit a planet. It orbits a star. Next, we examine the Shkadov Thruster, a stellar engine that uses reflected sunlight as thrust. We ask what it could move, how fast, and what it would cost. We also ask what it would look like from light years away, and whether the sky already contains such artifacts. The sun may be our ship, the galaxy may be our sea. The hazards in Chapter 1 were not hypothetical. They were a map of pressures that build over time, quietly and relentlessly, until even a stable orbit can become a liability. If the galaxy can shove the solar system, then a civilization may try shoving back. The opening hook becomes an engineering question, but it also becomes a philosophical one. What if the only way to save Earth is not to flee into interstellar darkness? What if we steer the sun itself and keep the planets as passengers, preserving oceans, ecosystems, and history? That proposal sounds like myth until you remember what the sun already is. It is a continuously operating power source, radiating in every direction, and it has been doing so for 4.6 billion years. The question is whether that steady flood can be given a preference, just enough to matter. On screen, the solar system is no longer a static diagram. It becomes a ship without a hull, drifting through a changing gravitational sea, while distant stars slide past like slow snow. In that view, propulsion is not a rocket plume. Propulsion is a bias, a tiny preference in how a star sheds its light. In 1987, Soviet astronomer Leonid Shkadov proposed a minimal stellar engine at the edge of what engineering even means. It does not burn fuel. It does not throw reaction mass. It uses the star's own light as a lever, and it asks time to do the heavy lifting. The late Cold War context matters because it shaped how scientists thought about scales. Spaceflight had already made orbital mechanics practical, and astrophysics had already made stellar lifetimes feel tangible. Shkadov's idea sits between those worlds, part celestial mechanics, part megastructure speculation, and part sober momentum accounting. It also arrived in an era when big structures had a strange legitimacy. Concepts like Dyson spheres and solar sails had circulated for decades, and the mathematics of radiation pressure was already familiar from spacecraft design. Shkadov's move was to connect those ingredients to stellar motion, not just to probes. The Shkadov Thruster is a passive stellar engine, and passive is not a marketing word. A gigantic mirror sits near one stellar pole, and it partially encloses the star like a tilted bowl. It reflects a fraction of photons back, and the star's own radiation field becomes the working fluid. Visually, imagine a crescent of polished material hovering above the star's limb. The mirror is not a full Dyson sphere, and it does not swallow the sun in darkness. It is a partial shell, a bright arc against the glare, with a shadowed interior that never quite touches the photosphere. As the camera pushes in, the scale becomes unsettling. The arc is wide enough to eclipse continents, yet thin enough to look like a blade. Along its rim, the reflected glare blooms into a hard white line, and the star's limb darkening becomes visible as a gradient. The core claim sounds like a trick because it contradicts everyday intuition. Light has no rest mass, yet it can push, and the push is real enough to steer spacecraft. The push is small, but it never stops because the star never stops shining. Photon momentum is the entry point, and it is one of the cleanest equations in physics. A photon with energy E carries momentum P equals E over C, even though it cannot be at rest. That momentum is not optional because it is built into how electromagnetic waves carry energy through space. In plain terms, energy flow implies momentum flow, and momentum flow implies force when you change it. This is why sunlight can torque a satellite, and why engineers paint spacecraft surfaces with careful optical properties. The same bookkeeping scales upward even when the source is a star. When light is absorbed, momentum is transferred to the absorber, and the absorber feels a force. When light is reflected, momentum reverses direction, and the change is larger. The mirror does not need to grab photons, it only needs to redirect them, and the bookkeeping does the rest. Radiation pressure is that force spread over area, and it is why comet tails point away from the sun. For perfect absorption, pressure scales with flux divided by c, which is already tiny at planetary distances. For perfect reflection, the momentum change doubles and pressure roughly doubles, which is why reflectivity is not a detail. A star emits power as luminosity L, and the sun's luminosity is a number we can measure precisely. If you could redirect all photons into one direction, the maximum thrust is L over c, a limit set by relativity and conservation laws. Real designs capture only a fraction, so thrust is smaller and the fractions matter. This is why the Shkadov Thruster is called passive, even though the structure itself is anything but simple. The engine does not add energy, and it does not tap the star's nuclear fuel directly. It only biases where the star's existing energy goes, turning isotropic emission into slightly anisotropic emission. That word, anisotropic, means the star stops being perfectly fair. In a normal star, photons leave in all directions, and the momentum vectors cancel. With a mirror in place, the cancellation becomes imperfect, and the leftover becomes a net push, like a constant breeze that never changes direction. The mirror is not a simple sail drifting outward, because a drifting sail would not hold a stable geometry. It is closer to a statoid concept, a structure that can hover by balancing forces rather than orbiting. In that regime, Up is away from the star, and down is gravity, and the balance is delicate. Gravity pulls the mirror toward the star with a force that depends on distance and mass. Light pressure pushes it away with a force that depends on flux, area, and reflectivity. At the right distance and angle, those forces can cancel, leaving a quasi-stationary structure that does not need orbital speed. On screen, this is a strange kind of hovering. Panels hang above a boiling photosphere, not falling in and not flying away, as if pinned in place by invisible hands. The star rotates beneath them, granulation patterns crawling across the surface like living cells, while the mirror holds its tilt. The geometry matters because the star is a sphere of emission, not a point lamp. If the mirror sits near the equator, symmetry fights you, and the planetary plane becomes a source of interference. Forces and torques couple strongly to orbital planes and can destabilize the configuration, especially over long times. Placement near a pole reduces interference with the planetary plane, and that is not just convenience. It also makes the thrust direction easier to align with the star's spin axis, which is a natural reference line for control. That alignment helps long-term stability and simplifies control, because precession and seasonal perturbations become easier to predict. There is also a quiet observational reason to prefer a pole. The planets mostly stay in the ecliptic, so a polar structure can avoid casting complex, time-varying shadows across inhabited worlds. The mirror can do its work without turning every year into a new pattern of eclipses. The mirror is shaped like a shallow, curved segment, and curvature is doing real work. It intercepts a cap of the star's output and reflects it back toward the photosphere, rather than scattering it into random space. The reflected light is then re-emitted thermally, but not perfectly symmetrically, because the boundary conditions have been altered. That asymmetry is the engine, and it is subtle enough to be missed in a casual explanation. Photons leaving the star carry momentum, and momentum must be conserved. If more momentum leaves in one hemisphere than the other, the star recoils in the opposite direction, and the recoil is continuous. The mirror does two things at once, and the combination is why the design works. It blocks some outward photons on one side, preventing them from carrying momentum away in that direction. It also returns energy to the star, changing where and how radiation escapes, which shifts the effective bright spots of emission. In the simplest picture, the net thrust is set by the blocked fraction of luminosity, and that is a useful first estimate. If the mirror covers a fraction f of the star's sky, thrust is on the order of F times L over c. The real thrust depends on reflectivity, curvature, and thermal re-radiation patterns, but F sets the scale. A helpful visual is vector arrows drawn on a glowing sphere. Without the mirror, arrows radiate outward evenly, and the sum is 0. With the mirror, arrows on the covered side are shortened or redirected, and a small leftover arrow remains, pointing like a compass needle. The mirror must also survive the environment it creates, and this is where the romance of the idea meets the cruelty of heat. It sits close enough that sunlight is intense, far beyond anything experienced near Earth. It must be ultralight, highly reflective, and thermally managed to avoid melting, buckling, or slowly creeping out of shape. Even highly reflective is not enough, because absorption of a few percent becomes catastrophic at stellar flux. Any absorbed energy becomes heat that must be radiated away, and radiating away heat requires temperature. Temperature drives material stress, and stress drives failure, especially across structures that span planetary scales. The thermal problem is not only peak temperature but gradients. One side faces a brutal radiative bath, while the other side looks into cold space, and differential expansion tries to twist the surface. Over decades, that twist becomes misalignment, and misalignment becomes lost thrust, or worse, runaway torque. A single rigid dish is not realistic at stellar scales, because rigidity is expensive in mass. The structure must be segmented into many panels, and segmentation is not merely practical. Each panel can be tensioned, phased, and replaced, like a swarm that behaves as one mirror while tolerating damage and gradual degradation. On screen, the mirror becomes a glittering archipelago. Millions or billions of facets flash as they adjust, each one a small machine with a simple job. From far away, the swarm reads as a smooth curve, but up close it is a moving field of metal and carbon films. Control becomes the hidden requirement, and it is the part that turns a concept into a civilization. The mirror must hold its angle to maintain thrust direction, and it must do so while buffeted by variable radiation pressure. It must damp oscillations and resist drift, because small tilts can create torques that grow over time. A statite equilibrium is conceptual, not magical, and it comes with fine print. It assumes active station keeping at the margins, correcting errors before they amplify. A civilization would need distributed sensors, autonomous actuators, and fault tolerance measured in millennia, because a slow failure can be as deadly as a fast one. Now connect this to the central question, which is not about cleverness, but about plausibility. Can an advanced civilization realistically use stellar engines to pilot an entire solar system away from hazards? The Shkadov Thruster is the gentlest test case, and gentleness is the point. The thrust is continuous but tiny, and the numbers force humility. For a Sun-like star, L is about 3.8 times 10 to the 26 watts, a flood of energy that powers climates and photosynthesis. L over C is about 1.3 times 10 to the 18 newtons, which sounds enormous until you remember what it must move. That number sounds huge until you divide by the Sun's mass, and the Sun is almost all the mass in the solar system. The Sun weighs about 2 times 10 to the 30 kilograms. The resulting acceleration is around 10 to the minus 12 meters per second squared, an acceleration you would never feel, even in a lifetime of measurement. If the mirror captures only a fraction, acceleration drops further, and realistic F values matter more than optimism. Even optimistic coverage yields an acceleration that is still far below anything in human intuition. The engine is patient by necessity, and patience becomes a design parameter. To make that slowness intuitive, compare it to familiar accelerations. Gravity at Earth's surface is about 10 meters per second squared, and even a gentle elevator is a fraction of that. The Shkadov acceleration is roughly 1 trillion times smaller, yet it acts without pause day after day, epoch after epoch. But constant acceleration compounds, and compounding is the secret that makes the idea serious. Over 1 million years, about 3 times 10 to the 13 seconds, delta V is a times t. At 10 to the minus 12, that is tens of meters per second, a speed change large enough to matter in galactic dynamics. Over 10 million years, the gain becomes hundreds of meters per second, and the trajectory begins to diverge noticeably from an unpowered star. Over 100 million years, it becomes kilometers per second, which is comparable to the velocity dispersions that separate stellar populations. The Shkadov Thruster trades urgency for inevitability. On screen, a timeline scrolls while the Sun's path bends imperceptibly. The curve is so gentle it looks like a straight line, until the camera zooms out to tens of millions of years. Then the deviation becomes a new track across the Milky Way, like a ship altering course far offshore. It is worth pausing on what course means in a galaxy. The Sun is already orbiting the Milky Way at roughly 200 kilometers per second, and it bobs through spiral structure and stellar neighborhoods. A few kilometers per second added in a chosen direction is not dominance, but it is agency. This is excellent for long-term stellar kinematics control, and it fits the timescales of slow hazards. It is useless for last-minute evasions, and that is not a criticism but a boundary condition. It cannot dodge a sudden threat on a century timescale, because the thrust is too gentle to matter quickly. The slowness is not a flaw if the civilization thinks in deep time, and deep time is the chapter's unspoken unit. Chapter 1 framed hazards on million-year clocks, where small changes accumulate into existential outcomes. A million-year engine is a rational response to million-year risk, provided someone is willing to maintain it. The next concern is whether the planets stay with the Sun, and this is where intuition can mislead. If you push the star, do you tear the solar system apart? The answer depends on how slowly you change the gravitational frame, and on whether the change is smooth enough for orbits to adapt. The Sun's gravity defines the planetary orbits, and those orbits are solutions to a central force problem. If the Sun accelerates very slowly, the planets experience an almost uniform inertial force in the accelerating frame. Their orbits adjust adiabatically, like a system that is nudged without being shocked. Adiabatic here means the change is slow compared to orbital periods, and that is the crucial ratio. Earth's year is 1 year, and Jupiter's is 12, while Neptune's is 165. A million-year acceleration is effectively constant over billions of inner-planet orbits, so the system can re-equilibrate without violent resonances. The planets do not need to be dragged by a tether, because nothing is physically pulling them forward. They remain bound because the Sun's gravitational well moves with the Sun, and the planets remain trapped inside it. the center of mass shifts and the whole architecture follows, like beads sliding in a moving bowl. Still, there are subtleties that matter for a complete picture. A constant acceleration adds a small effective potential, like a weak uniform field superimposed on the inverse square gravity. It can slightly distort orbital elements and shift equilibrium points, especially for distant bodies where binding energy is low. In a visual simulation, inner orbits remain nearly circular, while the outer regions breathe and warp. Lagrange points shift by tiny amounts, and Trojan swarms drift slowly. Comets at the edge of binding can be nudged into new distributions, not by violence, but by persistent bias. The outer solar system is the sensitive region, and sensitivity is a polite word for fragility. The Kuiper belt and Oort cloud are loosely bound, and their members are already perturbed by passing stars and the galactic tide. Over long times, a changing galactic path and a small inertial bias can reshape their distributions, changing impact rates and comet injection pathways. Yet the key claim remains, and it is the reason the Shkadov Thruster belongs in a Save Earth narrative. For inner planets, the acceleration is so small that orbital disruption is unlikely. The engine's gentleness is what makes it compatible with keeping a living planet intact, rather than scattering it into chaos. This is the chapter's pivot from danger to audacity, and the pivot is powered by a familiar sensation. The same physics that makes sunlight harmless on skin makes it useful as propulsion, because the pressure is weak and steady. The weakness is the feature because it preserves the passengers, even as it moves the ship. Now the darker side of the design, because every bias has a cost. The mirror does not create thrust for free, and it cannot avoid interacting with the star's outer layers. It changes the star's radiative boundary conditions, reflects energy back toward the photosphere, and that has consequences that unfold slowly. A fraction of the star's output is returned inward, and the star must process that energy again. In practical terms, the outer layers must transport and re-radiate the extra heat, and that can shift temperature gradients. The star may respond with small changes in convection patterns, surface granulation, and magnetic activity, even if the core remains steady. For a main sequence star like the Sun, the core fusion rate is set deep inside by pressure and temperature, and it does not instantly respond to surface tinkering. The immediate response is likely in the atmosphere and envelope, not in the core. Still, even small perturbations can matter for climate, because climate integrates small changes over long periods. The mirror also blocks direct light in one direction, and that changes what the star looks like from afar. For an external observer, the star could look dimmer from some angles and brighter in infrared due to re-radiation from the mirror and warmed stellar surface. The technosignature question begins to emerge, not as a beacon, but as a statistical oddity. The light curve could become subtly asymmetric, especially if the mirror edge occults the disk during rotation. Spectral lines might show faint anomalies if the star's surface temperature distribution changes, and the infrared excess could resemble a partial Dyson-like structure. None of these are guaranteed, but all of them are plausible fingerprints of altered radiative geometry. For the planets, the risk is not simply dimming, because the mirror does not necessarily reduce total output. The risk is redistribution and feedback, because the star's energy can be re-emitted with a different angular pattern. If the mirror changes total luminosity only slightly, it can still change spectral output and solar wind behavior in ways that reach Earth. Solar wind is not just a stream of particles, and it is not constant. It is tied to magnetic fields, coronal heating, and activity cycles, and those can respond to changes in the outer boundary. If the mirror modifies the temperature structure near a pole, it could subtly influence large-scale magnetic topology, which would matter for space weather over centuries. There is also an extreme scenario, and it is extreme only in consequence, not in mechanism. If the mirror reflects energy back and causes the star to radiate more in other directions, the net insolation at Earth could rise. A small percentage increase sustained for long periods can shift climate baselines, and baselines are where ecosystems live. Climate is non-linear, and that non-linearity is the quiet villain in many planetary stories. A few percent more sunlight can amplify water vapor greenhouse effects, because warmer air holds more moisture and moisture traps more heat. Ice albedo feedback can flip states, and once ice retreats, darker oceans absorb more energy, accelerating the drift. Ocean heat uptake can delay the worst effects, and delay can be deceptive. The deep ocean can store heat for centuries, smoothing the curve while the system loads energy like a battery. Then thresholds are crossed, circulation patterns reorganize, and the change that looked gradual becomes abrupt on human timescales. If the warming is sustained long enough, the narrative reaches a grim physical limit. Warmer oceans evaporate faster, and water vapor becomes a dominant greenhouse gas which drives further warming. In the far end of that chain lies a moist greenhouse, and beyond that a runaway greenhouse, where oceans can be lost to space over geological time. The narrative tension is simple, and it is the kind of tension engineers fear. The engine that saves the system from galactic hazards could endanger the biosphere through slow heating, even if no one intends harm. A civilization would need to manage propulsion and habitability together, because the sun is not just a mass to move, it is a climate engine. Mitigation is possible in principle, and the principle is control of degrees of freedom. The mirror's coverage fraction can be tuned, and the thrust direction can be adjusted to spread thermal effects over time. Additional shades or orbital mirrors could compensate at planetary distances, trimming insulation while the star is being steered. Those compensations have their own physics, and the physics is unforgiving. A planetary shade must be positioned with precision, and it must survive micrometeoroids and radiation. It must also avoid destabilizing resonances with Earth's orbit, and it must remain effective across precession and seasonal geometry. In deep time, even maintenance becomes a climate variable, but every mitigation adds complexity, and complexity adds failure modes that multiply rather than add. A million-year project must assume wars, collapses, and mistakes, and still remain safe. The engineering problem becomes governance across deep time, because the structure must persist through cultural discontinuities. That governance problem is not a new topic, but it is the shadow behind every technical diagram. Who decides the thrust vector, and who audits the thermal impact? Who notices a slow drift in mirror alignment before it becomes a century of extra heating? In a project measured in eons, even routine maintenance becomes a civilizational ritual. Mirror area requirements push you towards swarm architecture, and the arithmetic is blunt. To intercept a meaningful fraction of a sun-like star, you need an area comparable to the star's cross-section times that fraction. That is on the order of 10 to the 18 square meters, a number so large it stops feeling like engineering and starts feeling like geography. Mass constraints are brutal, and they force material science into the foreground. If the mirror has even grams per square meter areal density, total mass becomes asteroid scale or larger. The structure must be ultra-thin, likely measured in micrometers, and likely assembled from vast amounts of processed material harvested from moons, asteroids, or even dismantled planets. This is where megastructure talk becomes concrete, because it stops being a metaphor. You do not build one object, and you do not launch it from a single world. You build an ecosystem of machines, spread across the system, turning rock into film, film into panels, and panels into a coordinated surface. Mining, refining, manufacturing, and autonomous repair become the real engine behind the engine. The mirror is only the visible face, the bright geometry near the star. Behind it lies logistics, energy supply, and the slow choreography of moving mass across astronomical distances with minimal waste. The bottleneck is not only materials, and it is not only energy, because the sun provides energy in abundance. It is control, because a segmented mirror must act like a coherent surface under constant photon pressure. It must survive micrometeoroids, thermal cycling, and radiation damage without drifting into instability, and it must do so while individual units fail. Stability has to be designed, not assumed, and it must be designed for the long haul. The mirror experiences torques from imperfect reflection, and from the star's non-uniform emission, because stars have spots, faculae, and bright regions. It must actively correct its attitude, or it will precess and lose thrust alignment, turning a steering engine into a wobbling hazard. There is also a deeper control issue that hides inside the word swarm. If the mirror is made of countless panels, then the system is a network, and networks have modes. Some modes are stable, some are oscillatory, and some are catastrophic, where small delays in feedback produce growing waves of misalignment. The control architecture must anticipate those modes. The star itself is not perfectly quiet, and the sun is a reminder of that. Solar activity changes luminosity slightly, and changes particle output dramatically, and even small luminosity changes alter radiation pressure. Over long periods, magnetic cycles and flares add noise to the force balance, requiring robust feedback control that can handle both steady drift and sudden impulses. On screen, the mirror's edge trembles with tiny adjustments during a flare. The star brightens in ultraviolet, and the radiation pressure spikes, and the panels respond like a school of fish. The motion is graceful when control works, and terrifying when it does not because the star is always there beneath them. So the Shkadov Thruster is both simple and impossible, and that contradiction is the point of the chapter. Simple in physics because it is just momentum conservation applied patiently. Impossible in practice without a civilization-scale industrial base, and a culture that treats 1,000,000 years as a planning horizon, not as an abstraction. That returns us to detectability, because a structure that large cannot be perfectly invisible. A partially enclosed star could show an infrared excess from waste heat, because absorbed energy must go somewhere. It could show an unusual light curve if the mirror edge occulted the disk, and it could show kinematic anomalies if the star's motion deviated from local populations. Kinematic anomalies are especially intriguing because they are cumulative, and they are hard to fake naturally. In a stellar neighbourhood, stars share velocity distribution shaped by galactic dynamics and birth clusters. A star that slowly accelerates in a preferred direction might drift out of those distributions, not dramatically, but enough to become a statistical outlier over time. But the signature is subtle if coverage is modest, and modest coverage may be the rational choice. The thrust is small, so the structure can also be small, and small structures are easier to manage thermally. A civilization could build a weak thruster that is hard to notice, yet still meaningful over tens of millions of years, and that possibility complicates any search strategy. The central question tightens, and it becomes almost uncomfortable in its implications. If such engines exist, they may not announce themselves as bright beacons. They may look like slightly odd stars drifting with slightly odd velocities, wrapped in slightly too much infrared, and only a careful survey would notice the pattern. And that raises a final, unsettling observation. If we ever detect a star whose motion looks gently purposeful, we will have to ask what danger it is avoiding. We will also have to ask what it is trying to carry with it, because passengers imply something worth saving. The Shkadov Thruster is the baseline, and baselines are valuable because they define what minimum means. It shows that a star can be pushed without fuel, using only the momentum of its light. It also shows the price of gentleness, because the universe charges interest in time, and the interest rate is measured in epochs. Now the transition to what comes next, because the ladder has more rungs. If passive propulsion is too slow, or if thermal side effects threaten habitability, a civilization may choose a harsher approach. It may turn to active stellar engines that convert stellar mass into directed exhaust, trading elegance for power. The story moves from mirrors to mass, and the tone shifts with it. The next chapter will ask how you mine a star, and what it means to turn fusion fuel into thrust deliberately. Passive light pressure is the first rung on a ladder of escalating power, and every rung changes what engineering is allowed to mean. Passive propulsion taught us patience, but it also exposed a ceiling on control, responsiveness and speed. A Shkadov mirror can bias starlight, yet the sun still radiates almost symmetrically across the sky. The push is real, but it is gentle, more like a slow tide than a decisive shove. Even a perfectly aligned mirror cannot escape the basic geometry of a glowing sphere. If the hazard clock runs faster than millions of years, a civilization looks for stronger levers. Active stellar engines are that escalation, and the shift is as conceptual as it is mechanical. They generate thrust by directing mass or high-energy exhaust, not by reflecting photons off of our sail. The principle remains momentum conservation, but the working fluid changes from light to matter. Matter carries far more momentum per unit energy at non-relativistic exhaust speeds, which is the regime most engineering prefers. In plain terms, throwing mass is usually a stronger push than redirecting light. Rocket intuition translates cleanly, even when the vehicle is a star and the nozzle spans solar radii. Thrust is mass flow times exhaust velocity, and acceleration is thrust divided by stellar mass. The rocket equation lurks behind every proposal, because it is bookkeeping for momentum and energy. It also hides a warning. Propellant that leaves the system is gone forever, and the bill is paid in mass. If you can increase exhaust velocity or mass flow, you can reshape the trajectory faster, at a price. Radiation pressure is limited by L over C, and that limit is brutally simple. A star's luminosity is immense, yet C is larger, and the ratio caps photon thrust even for perfect reflectors. With mass ejection, the same power can drive much higher momentum if exhaust is slower than light. That trade is the heart of active stellar engineering, and it is why engines tempt impatient civilizations. The trick is not free energy. It is choosing how momentum is packaged and exported. The story darkens here, because active engines consume and rearrange stellar material deliberately, rather than merely redirecting sunlight. They are not just sails drifting in a clean beam. They are plumbing, reactors, magnetic nozzles, and control systems operating near a photosphere. They promise steering authority, but they demand the ability to survive where stars are trying to destroy structures. The sun is not a backdrop. It is a corrosive, eruptive environment that never turns off. Define the category clearly, because the label hides multiple architectures. An active stellar engine is any system that produces net thrust by expelling directed reaction mass or beamed energy. The star becomes both propellant tank and power plant, either directly or through harvested feedstock. The engine's signature is anisotropic outflow rather than anisotropic illumination, and that difference matters for detection. When a star throws material in one preferred direction, it stops looking like ordinary stellar weather. Start with the Kaplan thruster, because it is the canonical active design for a sun-like star. It keeps the star intact while adding an external propulsion apparatus, like a detachable organ built around a living heart. It uses collected hydrogen and helium as fuel and reaction mass, then throws that mass away in a controlled direction. Unlike a mirror, it can also steer in multiple axes, which turns drift into navigation. In the visuals, it reads like a halo of machinery shaping a star's breath. The Kaplan concept begins with collection, and the visuals are almost biological. You gather material from the solar wind, from the corona, or from mined bodies delivered inward on carefully timed orbits. Solar wind capture sounds easy until you do the numbers, because the wind is diffuse and fast. Typical densities are so low that scooping becomes an exercise in sheer area, not in cleverness. To gather meaningful mass, you need vast electromagnetic scoops spread across enormous cross-sections, like invisible nets woven from magnetic field lines. Those scoops are already a megastructure project, and not a delicate one. They must survive hard ultraviolet, X-rays from flares, energetic particles, and micrometeoroids moving like rifle rounds. They must maintain field geometry, while the sun's magnetic environment shifts beneath them. They must also compress and route plasma without letting it short-circuit, reconnect, or escape in turbulent bursts. The collection system becomes a distributed industrial organism, not a single device. It would look less like one machine and more like a coordinated ecology of machines. Even the act of scooping plasma hides difficult plasma physics that textbooks treat as warnings. Charged particles spiral along magnetic field lines, but they also drift, scatter, and heat as fields change. A scoop that is too strong can trigger instabilities, and a scoop that is too weak simply leaks. The structure must shepherd a collisionless flow into something that behaves like a pipe, an odd demand in a near vacuum. Every kink in the field becomes a potential turbulent seed, and turbulence is where control quietly dies. Then comes processing, where the engine stops looking like a net and starts looking like a refinery. Captured plasma must be cooled, separated, and fed into a fusion system at controlled rates. Cooling is not trivial, because hot plasma does not like to become cold gas on command. Separation is also not trivial, because ionized mixtures behave like fluids and like electromagnetic noise at the same time. Hydrogen is abundant, but fusion is not a simple fire you can light and forget. The reactor must sustain confinement, manage instabilities, and handle neutron and gamma loads if advanced cycles are used. Every subsystem is forced to work at scale, because a star's inertia makes small engines irrelevant. The sun is not a spacecraft that you can nudge with a brief burn. It is a gravitational anchor for billions of bodies, and its mass is the definition of stubbornness. So the Kaplan thruster is not one reactor. It is likely a network of reactors, compressors, and field generators acting in concert. In the imagery, you would see long arcs of plasma being guided inward, then vanishing into bright controlled throats of fusion light. The baseline fusion pathway is the proton chain, because that is what the sun already runs deep in its core. But the proton chain is slow, and it is slow for a reason. Quantum tunneling through the Coulomb barrier is rare at ordinary densities. The Sun compensates with immense pressure and time, which a compact reactor does not have. Historically, this was one of the great revelations of 20th century astrophysics. Stars shine steadily because their fusion is throttled by probability. A civilization would likely use faster pathways, like deuterium, tritium or deuterium, helium-3, if it can source isotopes and tolerate the radiation profile. The choice of fusion cycle sets the engine's personality, because it sets what the exhaust looks like. Tritium yields high power but produces fast neutrons that punch through materials and breed activation. Deuterium, helium-3, shifts more energy into charged particles, which are easier to collimate magnetically. Even then, the reactor must reject waste heat because no conversion is perfect, and entropy always collects its tax. Waste heat is not a side effect. It is a design driver that determines radiator area and operating temperature. Energy conversion limits appear immediately, and they are not negotiable. Fusion does not turn all mass into usable exhaust energy, and much energy becomes heat in structures and magnetic coils. Even with ideal conversion, you cannot beat momentum bookkeeping. You can move a star only by exporting momentum, and exported momentum must be carried by photons or by mass. The engine's elegance is measured by how little of its power becomes mere warmth. In a close-up visual, radiators would glow dull red in infrared, quietly bleeding away the cost of control. Kaplan's key move is to turn fusion energy into a collimated jet, because direction is everything. Collimation is the difference between a fire and an engine, and it's also the difference between thrust and chaos. A wide plume wastes momentum sideways and adds torque you did not ask for. A narrow jet concentrates thrust, reduces unwanted rotation, and makes steering predictable across millennia. The jet is not just exhaust, it is a vector drawn across interstellar space. Nozzle physics becomes the bottleneck, because the exhaust is too hot and too erosive for ordinary materials. Near a star, solid nozzles are limited by temperature, sputtering, and relentless particle bombardment. Magnetic nozzles are plausible, but they demand stable fields over enormous scales. They must guide plasma without touching it, while resisting reconnection events and turbulence that can tear a jet into ragged filaments. The nozzle is not a part, it is a controlled region of space. If the field stutters, the engine stutters, and the star's motion becomes a long-term wobble. Exhaust velocity sets the performance regime, and it forces a trade that never goes away. If exhaust is only tens of kilometers per second, thrust is high for a given mass flow, but efficiency is low. If exhaust is thousands of kilometers per second, efficiency rises but thrust drops unless mass flow increases. The design becomes a balancing act between power, propellant supply, thermal management, and desired acceleration. In practice, the best exhaust speed depends on how urgent the threat really is. The engine is tuned not only to physics, but to a civilization's risk tolerance. Kaplan's advantage is controllability, and that is why it is often presented as the civilized option. You can modulate thrust by changing mass flow and reactor power, like throttling a rocket that happens to be star-sized. You can steer by gimbaling magnetic fields or by operating multiple jets in coordinated patterns. You can also shut it down quickly compared to a mirror, which is a governance advantage in a system with inhabited worlds. The ability to stop matters as much as the ability to start. In a system with politics, abort is a feature, not a luxury, but controllability does not remove consequences, because the engine operates inside a living heliosphere. Any sustained jet interacts with the solar wind, the heliospheric current sheet, and the magnetic bubble that shields planets from cosmic rays. It can change particle flux, magnetic topology, and radiation exposure in ways that are hard to predict. The engine is not just moving the sun, it is changing the space weather of the entire system, and those changes ripple outward. A small change in the sun's magnetic environment can become a large change in a planet's radiation dose. Imagine the visual, a bright, needle-thin plume stabbing into darkness, while the rest of the heliosphere warps like a sail in a storm. Auroras intensify on magnetized worlds, then fade as field lines reconfigure. Dust grains charge and drift, and comet tails bend in unfamiliar directions. The sky itself becomes an instrument panel, displaying the engine's influence in slow motion. Even the zodiacal light would subtly skew, as charged dust responds to altered electromagnetic currents. Now widen the frame to scientific grounding, because the romance of megastructures still obeys arithmetic. Active engines are constrained by the same limits as rockets, only scaled to stellar mass. The Sun is 2 × 10 to the 30 kilograms, and that inertia is unforgiving. To get meaningful acceleration, you need either enormous thrust or immense patience. Active engines buy you more thrust, but they also demand immense mass throughput and long-term stability. The question is not whether thrust exists, but whether it can be sustained without cascading failure. Mass throughput is where the megastructure reality becomes unavoidable and where many proposals quietly fail. Solar wind mass loss is real, yet it is small compared to what you would like for propulsion. The Sun loses on the order of 1 billion kilograms per second, which sounds huge until you compare it to stellar mass. Convert that into acceleration, and you discover how quickly huge becomes glacial. If you rely only on wind capture, acceleration is limited, and the timescales stretch back toward passive mirrors. If you supplement with mined material, you're effectively feeding the engine with planets. That leads naturally to starlifting, which is both resource extraction and propulsion in the same breath. If you can extract material from the star itself, you can raise mass flow dramatically and choose what you remove. You can tailor composition, pulling hydrogen for fuel and heavier elements for construction. Historically, starlifting entered the conversation as a way to extend stellar lifetimes and harvest rare isotopes. Here it becomes something sharper, an engine that runs on the star's own body. The same act that harvests resources also changes the star's future, and that duality is the danger. Introduce the Svoronos star tug as the more extreme branch of this logic, because it embraces the star as propellant. Instead of adding external propellant, you pull plasma directly from the star and use it as reaction mass. The star becomes the propellant reservoir, and the engine becomes a controlled leak. The thrust can be far higher because the available mass flow is far higher, and because you're no longer limited to what the wind happens to give you. In the visuals, the tug looks like a deliberate solar prominence that never falls back. The Svoronos idea is brutal in its simplicity, and the brutality is part of its appeal. Extract stellar plasma through magnetic structures that reach into the corona, where loops already rise and fall like luminous arches. Accelerate that plasma and expel it as directed jet, turning a natural outflow into a deliberate exhaust. Every kilogram expelled carries momentum, and the star recoils in the opposite direction. The star is tugged by its own escaping skin. The engineering challenge is to keep the extraction stable when the corona itself is a storm of reconnection. Higher mass flow increases thrust linearly, and that linearity is seductive because it feels like control. If you can lift and eject orders of magnitude more mass than the solar wind provides, you can accelerate the star faster. Over millions of years, even tiny accelerations integrate into large velocity changes. Over tens of millions, the star's galactic orbit can be significantly rewritten, and the map of future encounters changes with it. A civilization is no longer merely surviving time. It is editing its trajectory through the Milky Way's crowded lanes. But higher mass flow also means higher intervention, and intervention has side effects that do not stay localized. Removing mass changes stellar evolution, because mass sets luminosity, radius, and lifetime. A Sun-like star losing mass will adjust its internal pressure balance, and the response depends on how quickly you remove material. If removal is slow, the star can relax and re-equilibrate. If removal is fast, you can force structural changes that look, from a distance, like unnatural aging. Planetary climates respond to luminosity changes, and habitable zones shift like moving shorelines. Mass removal also changes gravity, and gravity is the quiet infrastructure of every orbit. If the Sun loses mass gradually, planetary orbits expand adiabatically, and orbital periods lengthen. The change may be gentle, but it is persistent, and persistence is how small shifts become history. Resonances can drift, Trojan swarms can loosen, and the architecture of minor bodies can rearrange. A propulsion plan can become an orbital engineering plan, and the bill arrives in dynamics rather than heat. The question becomes, can you keep a solar system orderly while its central mass is being intentionally trimmed? Angular momentum exchange becomes a second hidden constraint, because stars are not static spheres. Extracting plasma through magnetic fields can torque the star, spinning it down or up depending on geometry. Spin affects magnetic activity and wind structure, which feeds back into extraction stability. A civilization might need to manage stellar rotation as carefully as thrust direction, using counter-torques and phased extraction to keep the dynamo within safe bounds. In other words, you do not just steer the star's path, you steer its internal temperament. The visuals here are unsettling. Magnetic tethers anchored in a boiling corona, bright knots of plasma sliding along invisible rails. The jet pulses as instabilities rise, then damp as control systems respond. On the star's surface, active regions migrate, and the pattern of sunspots changes like a heartbeat. The engine is not outside the star, it is entangled with the star's own weather. From a distant telescope, the star might look subtly wrong, as if its activity has learned a rhythm. Now connect these engines back to the central question, because the chapter is not a catalogue of clever thrust tricks. We're not asking whether thrust is possible, because physics allows it in principle. We're asking whether a civilization can pilot a solar system without destroying its own habitability. Active engines raise the possibility of faster evasion, but they also raise the risk of self-inflicted catastrophe. The steering wheel is attached to the furnace. When you turn it, the heat shifts with you. At this point, extend the logic toward relativistic propulsion, because deep time invites extreme endpoints. Relativistic propulsion means reaching a significant fraction of c, where time dilation and energy costs reshape intuition. At 10% of c, interstellar distances shrink in travel time, but the required momentum is enormous. For a star, the numbers become almost mythic, and the engineering begins to resemble astrophysics. You are no longer optimizing an engine, you are negotiating with the energy budget of a civilization across epochs. Frame it carefully, because relativity is not required for many survival scenarios. You do not need relativistic speed to avoid many galactic hazards, and you do not need to outrun light to change your fate. A few kilometers per second can change encounter statistics over tens of millions of years, shifting the odds of close passes and radiation events. But if the goal becomes migration between galactic regions, or escape from dense spiral arms, higher terminal velocities become tempting. The temptation grows when the timeline stretches beyond any single civilization's memory. At that scale, even slow becomes a kind of vehicle. Relativistic thinking changes navigation, and it changes what home means in the first place. The problem stops being a ship crossing space and becomes a star changing its kinematic membership. You're no longer launching missions from a fixed home. You're moving the home through the galaxy, and the galaxy becomes the map of currents and dangers. In that map, velocity space matters as much as position, and the destination is often a statistical environment rather than a single point. The question becomes strangely abstract. What region of phase space feels safest to live in? Even without full relativity, the kinematics perspective matters, and it changes what astronomers should look for. Stars are born in moving groups and drift into streams, leaving fingerprints in their velocities. A propelled star could depart those distributions, becoming a velocity outlier with a suspiciously steady acceleration. Detectability shifts from photometry to astrometry, because motion can betray intent over long baselines. The evidence is not a flash, it is a trend. A star that accelerates smoothly for millennia would look less like nature and more like policy. There is historical context in this shift, because astronomy itself has followed the same arc. Early observers mapped the sky as fixed constellations, then learned that proper motion exists, then learned that the galaxy rotates. In the 19th century, tiny shifts in star positions were already unsettling, because they implied a living sky. Now we can measure stellar velocities with exquisite precision, and we can ask a new question: what if some motions are engineered? The tools are already being built, even if the target is hypothetical. Our catalogues are becoming time machines, comparing the sky to itself. Now, introduce the Spider stellar engine, which exploits binaries as propulsion handles rather than fighting a lone star's inertia directly. In a binary, you have two masses exchanging energy and momentum through tides, winds, and radiation. If one object is a pulsar, the energy density is extreme, and the environment becomes violent. The pulsar's beam and particle wind can ablate a companion star, stripping its atmosphere into a comet-like tail. The system looks, in radio and X-ray light, like a laboratory for controlled damage. The Spider concept uses that ablation as thrust, and the mechanism is chillingly straightforward. The companion loses mass preferentially on the irradiated side, creating a rocket effect as gas streams away. The binary's centre of mass responds, and the system can accelerate as momentum leaves in a directed flow. The pulsar is not pushing with a mirror, it is pushing by stripping its partner, turning erosion into propulsion. The thrust vector is written into the geometry of illumination, like a spotlight that also burns. This is not hypothetical in the sense of physics, because nature already runs the experiment. Black Widow and Redback pulsars evaporate companions, and we observe the aftermath in radio eclipses and heated stellar faces. We see asymmetric winds, shocked plasma, and changing orbital periods that hint at mass loss. Nature demonstrates the mechanism, even if it does not aim it. The engineering leap is to control geometry and timing to turn ablation into a steering vector. That leap is smaller than inventing new physics, but it is still enormous in responsibility. Binaries offer unique control knobs, and those knobs are dynamical rather than structural. Orbital phase provides a periodic orientation, and you can modulate thrust by changing exposure, shielding, or the companion's outflow channels. You can also exploit gravitational slings within the system to redirect momentum exchange, using the orbit as a gearbox. Compared to a single star, a binary gives you more ways to couple energy into directed outflow. The system itself becomes part of the engine. It is propulsion by choreography rather than by brute force. But the cost is explicit sacrifice, and that is the ethical edge of the chapter. The companion is consumed to move the system, and consumption is not an abstraction here. If inhabited worlds orbit the companion, they are collateral, and the timeline may be short by stellar standards. Even if no one lives there, you're still dismantling a star to steer another. The question becomes uncomfortable. How much destruction is acceptable in the name of survival? And who gets to answer that question when the consequences last longer than any constitution? Now gather the risks and constraints into a single escalating list, because the chapter's tension depends on accumulation. First is stellar evolution impact from mass removal, which can shift luminosity, radius, and spectral output. Second is angular momentum exchange, which can alter magnetic activity and wind behavior in feedback loops. Third is destabilization of planetary climates through changing insolation and orbital expansion, which can force migration or artificial climate control. These are not side notes, they are existential engineering requirements. A civilization that cannot model these effects is not steering, it is gambling. Fourth is dynamical stability, and it is easy to underestimate because it looks like a footnote in celestial mechanics. Continuous thrust adds a small inertial field that can perturb distant reservoirs like the Kuiper Belt and Oort Cloud. Those regions are already sensitive to galactic tides and flybys. Changing the sun's kinematics changes which perturbations arrive, and when. A propulsion plan can alter comet influx rates, and comets are the galaxy's slow ammunition. The engine may dodge one hazard while quietly loading another. Fifth is engineering survivability, which is where elegant equations meet hostile reality. Collection structures, magnetic nozzles, and star-lifting loops must operate near intense radiation and plasma flows. Materials must resist sputtering, embrittlement, and thermal fatigue for millennia, not merely for missions. Control systems must handle faults autonomously, because no human maintenance schedule matches stellar timescales. The engine must survive boredom as well as catastrophe. It must also survive its own success, because steady thrust invites steady wear. Sixth is governance and ethics, because steering a star is steering a civilization's future. Moving the system implies choosing a direction, a destination, and a risk trade that may outlast any political order. It also implies deciding what can be sacrificed to fuel the motion, and what must be protected at any cost. A civilization might preserve Earth by dismantling Mercury, then preserve the Sun by dismantling something else. The engine becomes a mirror held up to values. When propulsion becomes policy, physics becomes morality made visible. Hold the narrative tension here, because the contrast is the point. Passive engines were gentle, but slow, and their danger was mostly missed opportunities. Active engines are powerful, but invasive, and their danger is self-inflicted instability. The same capability that can dodge a supernova neighborhood can also unmake a star's long-term stability. Survival technology becomes a test of restraint as much as intelligence, because power without discipline is just a faster way to fail. The most advanced engine may be the one used sparingly, with deliberate humility. bring back the documentary anchors, because the central question is still whether stellar engines are realistic and detectable. Active engines widen the design space and widen the signature space, which is good for engineers and good for observers. They can create jets, altered winds, unusual elemental abundances, and infrared waste heat from processing. They can also create time-variable asymmetries that look wrong when compared to natural stellar behaviour. The sky offers many false positives, but it also offers patterns that nature rarely sustains. A Kaplan-like system might show persistent collimated outflows, not explained by natural stellar activity, and the collimation would be the tell. A star-lifting tug might change mass loss rates and coronal structure in measurable ways, especially if the outflow is steady rather than flare-driven. A spider engine might sit in a binary with anomalous ablation patterns and unexpected acceleration of the system's barycenter. Each signature is subtle, but subtlety is what long surveys are built to find. The search becomes one of consistency, because engineering tends to repeat itself. Yet the most durable signature may still be kinematic, because motion integrates quietly over time. Over millions of years, a small but persistent acceleration produces a measurable deviation in velocity space. Gaia-like surveys can map stellar motions with precision, and future surveys can extend baselines and reduce uncertainties. The galaxy becomes a forensic dataset for intent, and intent leaves tracks in phase space. The question becomes, how many tracks would we recognize if we saw them? And how many would we dismiss as statistical oddities because the alternative feels too strange? But detectability also depends on discretion, and discretion is an engineering choice. An advanced civilization could choose low-thrust, low-signature operation, accepting longer timescales to reduce observability. It could also hide waste heat by radiating at colder temperatures with larger radiators, blending into dust backgrounds. The search becomes statistical, not cinematic, because the loudest engines are not necessarily the most common. Quiet strategies may dominate if survival includes staying unseen. In that universe, absence of evidence is not comfort, it is ambiguity. Now pivot toward the next chapter with a hard boundary, because the narrative needs a gate. Every active engine depends on structures that operate close to a star without failing and without triggering runaway interactions. That is not a minor materials problem, and it is not solved by scaling up familiar alloys. It is the gate that decides whether these ideas are engineering or only algebra. The difference is survivability under continuous assault. A star does not care about your design margins, and it does not negotiate. So the chapter ends on mechanics, because mechanics is where dreams either become machines or become cautionary tales. If you want to throw stellar plasma like propellant, you must hold magnetic fields like scaffolding and keep them stable for ages. If you want to run fusion at scale, you must build reactors that do not erode into vapor under neutron and gamma bombardment. If you want a million-year engine, you need materials that treat a star as a workplace, not as an apocalypse. You also need control systems that can detect a flare, reroute flows, and recover without panic and without pause. That requirement points forward because it narrows the plausible futures to those with extraordinary control. The plausibility of active stellar engines rests on metamaterials, extreme temperature structures, and megascale control systems that behave like living swarms. The next step is to ask what could possibly survive there, and what kind of civilization could keep it stable. The engine is not just a device, it is a long-lived relationship with a star. Every active engine is only as plausible as the materials and control systems that can survive near-star conditions. We started with a mirror that nudges a star almost politely, and we end with engines that mine it, burn it, and throw it. The sun is no longer just a light hanging in the sky. It is a machine you can rewire if you accept the consequences and if you can live with what that power makes you become. A stellar engine is easy to sketch and hard to build. Chapter 2 gave us thrust from biased starlight, and Chapter 3 escalated to engines that mine and throw mass. Now the story hits the same wall for every design. Near the sun, construction is not a metaphor. It is heat, radiation, impacts, and stress across structures that dwarf planets. In concept art, the mirror is a clean arc, a single confident stroke against black space. In reality, it is a landscape of failure modes that must be managed, predicted, and absorbed. Start with the environment, because it sets every requirement and punishes every shortcut. Close to a sun-like star, radiant flux rises as 1 over distance squared, so every inward step multiplies the thermal problem. A mirror that is comfortable at 1 AU becomes a furnace when moved inward, even if its reflectivity is world-class. The sunlight is not a gentle lamp. It is a flood of photons carrying momentum, energy, and a spectrum that reaches into destructive ultraviolet. Even if the structure never touches plasma, it sits inside intense UV and extreme particle weather. The sun is not only bright, it is chemically and mechanically erosive, and it never stops. Thermal load is the first brutality because it is both immediate and cumulative. A reflector that absorbs only 1% still turns 1% of stellar flux into heat, and that fraction scales mercilessly with distance. At near-sun distances, that absorbed fraction can exceed the heat flux inside industrial furnaces, and it does so across areas measured in continents. Temperature is not just a melting point problem. Temperature gradients drive warping, creep, and fatigue, and gradients are unavoidable on thin films. Even a slight tilt changes illumination, and that change becomes a hot stripe that migrates across the surface. The physics is simple. Where the photons linger, the lattice heats, and where it heats, the geometry shifts. In visuals, the mirror does not glow evenly. It blooms with uneven colour like heated metal in a forge. A thermal map would show bright seams where a coating is imperfect, and darker zones where radiators are doing their quiet work. The edge of a tile might run cooler than its centre, because edges radiate more effectively and conduct differently. Those differences matter, because a membrane is not a rigid plate. It stretches, it relaxes, and it remembers stress through slow deformation. Over years, that memory becomes creep, atoms sliding into new positions under constant load, as if the structure were slowly learning a new shape. Ultraviolet and X-ray radiation are the second brutality, and they attack at the molecular level. High-energy photons break chemical bonds, darken polymers, and change surface states, so the mirror's optical behavior can drift even if its shape stays perfect. Materials that survive in Earth orbit can embrittle when UV dose is relentless and unshielded. Because near the sun, the exposure is not occasional. Coatings that look stable for years can drift in optical properties over decades, and decades are a blink for a stellar engine. A million-year engine cannot treat degradation as a maintenance footnote. It must treat it as a design input, as fundamental as gravity. Even the idea of aging changes here, because the star provides a continuous quantifiable dose that never goes to zero. Particle radiation is the third brutality, and it is more physical than it sounds. Solar wind ions sputter atoms from exposed surfaces, one collision at a time, like sandblasting performed by a diffuse invisible storm. Coronal mass ejections add bursts of energetic particles that punch deeper and charge structures, and the charging is not merely an electrical nuisance. Charging matters because it creates electrostatic forces across huge areas, and those forces can wrinkle films and destabilize formation flying. A large sheet can behave like a drumhead that is being tugged by fields you cannot see. The result is a structure that twitches and flexes in response to space weather. In a wide shot, you would see the swarm shimmer, not from motion you commanded, but from motion the star demanded. Micrometeoroids are the fourth brutality, and they are the sharpest. Near the Sun, dust populations are faster and more energetic than in the outer system, because orbital velocities are higher and trajectories are tightly curved. A grain smaller than a millimeter can hit like a bullet at tens of kilometers per second, and the impact physics is closer to an explosion than a collision. The kinetic energy vaporizes material locally, creating plasma jets and shock waves that do not respect neat engineering boundaries. Impacts do not need to shatter the whole mirror. They only need to see tears that propagate under tension, or pits that roughen a surface enough to scatter light. In close-up, you would see peppering, tiny craters that turn a perfect optical surface into a matte one. And in the harshest light, you would see ejector plumes, brief and bright, like microscopic fireworks against the arc. There is a reason conventional spacecraft materials fail at megastructure scales, and it is not a lack of cleverness. They were designed for small areas and short missions, where redundancy can be heavy and maintenance can be scheduled. They tolerate damage by accepting loss of performance, because a probe can limp home with a degraded panel. A Shkadov-class mirror cannot accept cumulative loss the same way, because its thrust budget is a bookkeeping exercise in tiny percentages. Small percentage losses in reflectivity become large losses in thrust, and large gains in waste heat. A little darkening is not cosmetic. It is a thermal runaway risk. When absorption rises, temperature rises, and when temperature rises, coatings degrade faster, an acceleration loop that turns slow decay into sudden crisis. This is where metamaterials enter, not as magic, but as strategy and discipline. A metamaterial is defined by engineered structure-property relationships, meaning its performance comes from geometry and layering as much as chemistry. You do not ask a bulk material to be everything at once. You build a stack that behaves like the optical and thermal device you need, and you accept that different layers will sacrifice themselves at different rates. The word metamaterial carries a history of human ambition. Early optics relied on polished glass and metal, then on thin films, and then on engineered nanostructures that bend light by design. In the 20th century, multilayer mirrors and dielectric coatings turned interference into a tool, and later nanofabrication turned surfaces into carefully tuned landscapes. The same logic scales upward, if manufacturing can scale with it. The question is not whether light can be shaped, but whether industry can keep shaping it for deep time. For a Shkadov-like mirror, the key metric is reflectivity to mass ratio, because every kilogram must earn its place. High reflectivity reduces absorbed heat and increases photon momentum reversal, which is where thrust comes from. Low areal density keeps gravity and structural loads manageable, and it makes station keeping less costly in force. The ratio matters more than any single property like tensile strength. A heavy perfect mirror is worse than a light mirror that is almost perfect, because heavy structures demand more support and more correction. In a system measured in astronomical units, mass is not just mass. It is inertia, logistics, and time. It is also risk, because mass concentrates failure into fewer, harder-to-replace components. Candidate materials are chosen with that ratio in mind, and with the sun's chemistry in mind. Silicon nitride is a serious baseline because it sits in a useful middle ground of strength, stiffness, and thermal stability. It is strong and stable at high temperatures compared to many polymers, and it can be fabricated as thin membranes with good mechanical performance. It also tolerates radiation better than many organic films because its bonds are not as easily broken by UV. Silicon nitride is also a familiar material in microfabrication, used in membranes and windows precisely because it can be thin without becoming fragile. In imagery, a silicon nitride membrane is not a shiny foil. It is a pale, ceramic-like skin, thin enough to flutter if untensioned, yet tough enough to hold shape when pulled tight. Under grazing sunlight, it would show a faint milky sheen, like ice that refuses to melt. Titanium nitride is a second candidate, often as a coating rather than bulk, and its appeal is partly chemical. Tin is hard and chemically resistant, with good high-temperature stability, and it can reduce oxidation and surface erosion in harsh environments. Its optical behavior is tunable, which matters when you need reflectivity in specific bands and controlled emissivity elsewhere. TN also has a visual signature, golden in some thicknesses, though at megascale the colour is less important than the spectrum. The point is not beauty, the point is survival under bombardment. In close view, a tin-coated tile might look like a muted sunrise, but its real identity is mathematical, a curve of reflectance and emissivity that stays within tolerance. Coatings versus bulk is a central design choice, because the sun attacks surfaces first. Bulk materials carry structural loads and define tear resistance, so they decide whether a tile survives tension and impact. Coatings define optical reflectivity and emissivity, and they take the first hit from sputtering and UV. A thin coating can be replaced or renewed more easily than an entire membrane, especially if robotic servicing is routine. The architecture becomes a layered device with sacrificial surfaces, like ablative shielding that is designed to lose material gracefully. In a close shot, you would see a tile as a stack: substrate, adhesion layer, optical layer, protective cap, each one engineered for a specific job. Between layers, interfaces become their own battlefield, because differential expansion can shear bonds even when the bulk survives. Multi-layer stacks are where metamaterial thinking becomes practical rather than aspirational. Alternating layers can create high reflectivity through interference effects, where reflected waves reinforce each other at chosen wavelengths. The same stacks can be tuned to reflect visible light while emitting strongly in infrared, and that tuning is not aesthetic. It is thermal control, because the star's spectrum peaks in the visible for a sun-like star, while waste heat must be dumped in longer wavelengths. The mirror wants to behave like a one-way valve for energy, rejecting the star's light while letting its own heat escape. That selectivity can be engineered by thickness, refractive index contrast, and surface texturing that suppresses absorption pathways. The deeper insight is that optics becomes thermodynamics here, because every photon that is not reflected must be accounted for as heat. Waste heat becomes the constraint that refuses to go away, because perfection is not an option. No reflector is perfect, and absorbed power must be rejected, whether it is 1% or 1/10 of 1%. Rejection happens by radiation, which depends on emissivity and temperature, and the relationship is steep. If emissivity is low, temperature must rise to radiate the same heat, and that rise is not linear. If temperature rises, materials creep and buckle, and control becomes harder, because the mirror's shape becomes a moving target. The engine's thrust is born from light, but its longevity is decided by heat. Even the best coatings face microscopic defects, and defects are where absorption concentrates first. So emissivity engineering becomes as important as reflectivity, and it forces uncomfortable trade-offs. The mirror wants to be reflective where the star is bright and emissive where it can radiate waste heat, which implies surfaces that are spectrally selective. It also implies backside radiators that see cold space and stay optically decoupled from the star, so they are not heated by the same light they are trying to reject. In visuals, the front face is a bright arc, while the back face is a dark finned terrain, quietly glowing in infrared. The structure becomes two machines in one, an optical sail on one side, a radiator on the other. In the infrared view, the shadow side is not dark at all. It is a soft, persistent glow that tells the truth about energy. Radiative cooling surfaces cannot be an afterthought at this scale, because they set the operating temperature and therefore the mechanical regime. They also set the infrared technosignature, because waste heat must glow somewhere, and physics does not grant exceptions. A civilization can hide some signatures by radiating colder, over larger area, spreading the same power across more surface. That choice increases mass and complexity, and it makes the swarm harder to coordinate. The question becomes subtle. How much engineering would you accept to be less visible, and how much visibility would you accept to be simpler? And if you were watching from light years away, would you mistake deliberate coldness for natural dust? Or would the spectrum betray intent? Now move from materials to mechanics, because the mirror is not a lab sample and not a single object. A single solid mirror is impossible at stellar engine scale, not because we lack strong materials, but because the forces are differential. Tidal gradients across millions of kilometers create differential forces, so one side of the structure is pulled differently than the other. Thermal expansion across that span creates misalignment, even if the average temperature is controlled, because average means nothing to a thin sheet. Vibration modes become slow, huge waves that can grow if damping is weak, like ocean swells that cross an entire hemisphere. In the wide shot, the mirror is not rigid. It breathes. It also drifts through modes that last hours or days, because at this scale, even a gentle oscillation has nowhere to hide. Buckling is the silent killer for thin structures, and it arrives before any dramatic fracture. A membrane under compression will wrinkle long before it breaks, and those wrinkles are not small imperfections. Wrinkles change the local angle of incidence and scatter light, and scattering reduces thrust while increasing heating in unpredictable patterns. The mirror must be designed to stay in tension, and tension must be maintained despite impacts, creep, and thermal cycling. This is a mechanical truth that shipbuilders and bridge engineers learned early. Compression invites instability, while tension can be controlled. The near-sun problem simply magnifies that old lesson until it becomes existential. The solution is segmentation, because segmentation turns impossibility into statistics and maintenance into routine. Instead of one dish, you build millions of modular tiles, each one a small machine rather than a passive sheet. Each tile is small enough to manufacture, test, and replace, and small enough that its vibration modes are higher frequency and easier to damp. Each tile can be tensioned and shaped locally, and its optical coating can be tuned for its specific role in the global figure. The megastructure becomes a coordinated swarm that approximates a continuous curve, the way pixels approximate an image. From far away it looks smooth. Up close it is a mosaic. In close-up you would see seams, gaps, and alignment marks, evidence that the arc is assembled, not cast. Segmentation also changes failure modes, which is the real reason it matters. A micrometeoroid can destroy a tile without tearing the whole system, because the tear has nowhere to run. Sputtering can degrade a fraction of tiles while the rest remain effective, and that degradation can be mapped and compensated. Control can route around damaged regions by adjusting neighbouring angles, like adaptive optics correcting a distorted wavefront. The mirror becomes resilient by being incomplete, and by expecting incompleteness. The design philosophy shifts from prevent all failure to absorb constant failure. That shift is psychological as much as technical, because it treats damage as a steady-state condition rather than an emergency. But a segmented mirror only works if coordination is real, and coordination is its own engineering frontier. The swarm must hold a global figure, not just local attitudes, because thrust depends on the collective geometry. Tiles must know their position, orientation, and health state, and they must know it with precision that sounds absurd at planetary scales. They must communicate across light minutes with delays that cannot be ignored, so control cannot assume instant feedback. Autonomy is not optional, because human-in-the-loop control cannot scale, and because even a fast civilization cannot outpace light. The swarm must think locally and act locally, while still serving a global plan. In a visualization, you would see a web of laser links blinking between tiles, a quiet choreography of ranging pulses and status packets. This is systems engineering at astronomical scale, and it has a particular flavor of difficulty. The mirror is not one object. It is an ecology of parts with sensing, computation, and repair, and the ecology must be stable against cascading errors. It needs distributed metrology to measure shape and drift, using beacons, laser links, and constant cross-checking. It needs fault detection that assumes constant attrition, because the sun is always eroding something. It needs manufacturing pipelines that can feed replacements for millennia, and those pipelines must be robust to political and cultural drift. A long-lived engine is not only a machine, it is an institution. Historically, even Earth's longest projects depended on continuity of knowledge, and here continuity must survive not centuries but geological time. Now address control and station keeping, because thrust is useless if alignment drifts, or if the swarm slides out of position. Chemical propellant dependence is a dead end because a million-year project cannot rely on stored reaction mass for routine corrections. Even if propellant is mined, logistics become a constant tax, and every correction becomes an industrial event. The control system must use ambient forces, the same way a sailboat uses wind rather than carrying fuel for every tack. Near a star, the dominant ambient force is already present and already paid for. It is radiation pressure. The same photons that threaten to cook your mirror can, with care, hold it in place. Solar sailing principles scale naturally to this problem, and they offer a kind of elegance. Radiation pressure is already the working force of passive propulsion, providing the thrust that biases the star's momentum exchange. The same pressure can be used for attitude control and positioning, if tiles can modulate how they interact with light. If a tile changes its reflectivity or angle, it changes the local force vector, and that change can be used as a control input. That creates torque and lateral control without expending reaction mass, and it does so continuously. The mirror becomes a control surface, not just a reflector. In a clean diagram, it looks like a simple arrow, but in reality it is a field of tiny arrows that must add up correctly. At megascale, station keeping is a continuous negotiation between gravity and light, and the negotiation never settles. The equilibrium is not static because solar output varies, and the swarm geometry changes as tiles age, are replaced or reconfigured. Control must damp oscillations before they couple into global modes, because global modes are slow and powerful. A small phase lag across the swarm can produce a travelling wave of misalignment, and that wave can grow instead of fading. The consequence is not just inefficiency. The consequence is thrust direction error, which is the difference between steering a star and merely warming space. When you aim a force over millennia, a tiny angular mistake becomes a vast positional mistake. Kirigami mechanics offers a low propellant control lever, and it is a concept with deep roots. Kirigami uses cuts and folds to create reconfigurable surfaces, turning a flat sheet into a mechanism. Engineers have used related ideas in deployable space structures for decades, because folding is a way to pack large area into small volume. Here, the goal is not deployment alone. The goal is continuous reconfiguration under load, using geometry rather than motors. A thin sheet can change effective area without changing mass, and it can change stiffness and damping by shifting how loads are carried. The elegance is that the actuator is the pattern itself, designed into the material like a hidden hinge. Explain the control idea in simple terms, because the physics is intuitive once you see it. By folding or buckling in controlled patterns, a tile changes its projected area to sunlight, and that changes radiation pressure magnitude. It also shifts the center of pressure relative to the center of mass, because the light now pushes on a different effective shape. The offset creates torque, and torque changes attitude like a weather vane that turns into the wind. In a close-up animation, a tile would ripple through a pattern, one corner lifting, a crease forming, a fold locking, then relaxing back as the control demand changes. The motion is small, but the consequences accumulate, because the swarm applies it everywhere, all the time. Kirigami also enables steering without moving the whole swarm as a rigid body, which would be mechanically expensive. Tiles can create differential forces across the structure, and differential forces can tilt the effective mirror figure and adjust thrust vector. The same approach can counter unwanted rotation by applying distributed counter torques, so the swarm can resist spin-up from asymmetries. Sunlight becomes both force and fuel for control, because the control authority is drawn from the same photons that provide thrust. The engine is self-actuating in the most literal sense. It is also self-limiting because control authority weakens when reflectivity degrades, so the system must defend its own optical health. There is a second benefit that matters for survivability, and it is easy to miss in diagrams. Reconfigurable geometry can absorb shocks and damp vibrations, because a structure with adjustable stiffness can avoid resonance. A tile that can change stiffness can avoid resonant coupling with global modes, and it can shift its natural frequency away from dangerous bands. It can also relax tension locally after an impact, preventing tear propagation, then retention once repair is complete. Mechanical adaptability becomes a form of damage control like crumple zones in vehicles but distributed across a swarm. In a visual sequence, you would see a shock ripple outward, then fade as tiles subtly change posture to swallow the energy. Metamaterials and Kirigami intersect in a useful way, and the intersection is where the design becomes truly integrated. A multi-layer optical stack can sit on a mechanically reconfigurable substrate, so the optical surface stays reflective while the backing changes shape. The tile becomes a combined optical, thermal and mechanical device, with each function designed to support the others. That integration reduces part count, which reduces failure points, and it reduces the need for heavy actuators. In visuals, you would see a tile as a living panel, its face steady and bright, its underside flexing with controlled folds. The most advanced version looks less like a mirror and more like a smart skin, engineered down to the last interface. Still, every control method has limits, and radiation pressure is famously weak. Control authority scales with area and reflectivity, so a tile must be large enough to matter. If tiles are too small, their individual forces are tiny, and the control bandwidth becomes a problem because you need too many adjustments. If tiles are too large, they become hard to stiffen and hard to repair, and a single failure becomes more costly. The design must choose a tile size that balances manufacturing control bandwidth and damage tolerance, and that balance may shift with distance from the star. The swarm might not be uniform because the environment is not uniform. In the inner regions, you might prefer smaller, more replaceable tiles, while farther out you might accept larger panels that drift more slowly. Heat management also couples to control in non-obvious ways, and it can sabotage precision. A hot tile expands and changes curvature, which changes force direction, and that change can look like a steering command that nobody issued. If emissivity varies across the swarm, temperature varies across the swarm, and those variations create differential expansion. Temperature variation becomes a control disturbance that looks like random torque, and random torque is the enemy of stable pointing. Thermal uniformity becomes a navigation requirement, not just a materials preference. The mirror must be thermally quiet to be dynamically quiet. Even the choice of seam geometry matters, because seams can become thermal discontinuities that seed wrinkles. Radiation damage couples to optics and therefore to force, and the coupling is slow but relentless. If UV darkening reduces reflectivity, absorbed heat rises and pressure drops, so the tile becomes hotter and less useful at the same time. Over time, that creates thrust asymmetry unless compensated, and asymmetry can slowly rotate the thrust vector away from the desired direction. Compensation requires either replacing tiles or dynamically reweighting control laws, treating degraded tiles as different actuators. The swarm must know which parts are aging, and it must respond before the drift becomes global. This is where sensing becomes more than inspection, because it becomes prediction, the ability to see tomorrow's failure in today's trend. Sputtering couples to mass distribution, which sounds negligible until you integrate it over astronomical area. As atoms are knocked off surfaces, areal density changes slightly, and the change is tiny per square meter. Over huge areas, small changes integrate into meaningful mass shifts, and those shifts alter the gravity-like balance for statite-like hovering. The swarm must track its own mass evolution and adjust geometry accordingly, because equilibrium depends on mass as much as reflectivity. In a long-lived engine, even erosion becomes a bookkeeping problem. The mirror must keep accounts with the sun. The accounting is physical. Grams lost here become micronewtons lost there, and over time the vector sum changes. Micrometeoroids couple to topology, because punctures change how a membrane carries load. A puncture can vent trapped gases if any are used for deployment, and even without gas, it can change local tension. A tear can change tension lines and create wrinkles that scatter light, and the wrinkles can spread like a crease in fabric. Tiles must be designed to fail gracefully, with ripstop patterns and compartmentalized membranes, so damage remains local. Repair must be robotic and routine, not heroic. The swarm must treat impacts the way a city treats potholes, constant, expected, and fixable. In a repair visual, small service craft would drift in, clamp, patch, recoat, and drift away, leaving the global arc unchanged. All of this pushes towards swarm robotics, even if the word is not spoken yet because no other approach scales. Construction near the sun will be done by machines that can tolerate radiation and heat, and that can work without constant supervision. Inspection will be continuous because degradation is continuous, and because early detection prevents cascading failure. Repair will be distributed because the structure is distributed, and because travel time across the swarm is not trivial. The mirror becomes a living infrastructure rather than a finished artifact, and its completion is a moving target. It is always under construction. If you could speed up time, you would see a constant ant-like motion along the arc, a maintenance choreography as steady as the star's own rotation. The mysterious part is not whether materials exist in principle, because physics allows many combinations. The mysterious part is whether an entire industrial ecology can operate in that environment for deep time, with supply chains that do not collapse. A civilization must build not only a mirror, but a supply chain that never stops, and a culture that keeps caring. It must build standards, interfaces, and self-checking protocols that survive cultural drift. Because 1,000,000 years is longer than most civilizations have existed, the engine becomes a test of continuity, and continuity is rarer than technology. What does it mean to maintain a project when its builders will never see its end? What does it mean to design a machine whose primary operating mode is repair, and whose success is measured in the absence of catastrophe? Bring the central question back into focus, because it is the reason this chapter exists. Can an advanced civilization realistically steer a star, and could we detect that attempt from far away? This chapter suggests a filter that is not about physics. It's about materials, maintenance, and control at scales where failure is the default, and where repair is a permanent operating mode. If the filter is passed, the result is not a single shiny arc. It is a persistent, adaptive swarm, always adjusting, always replacing, always correcting. And if the filter is not passed, the star remains unmoved, not because thrust is impossible, but because endurance is. Detection follows from the same constraints, because constraints leave signatures. Waste heat must radiate, and radiators glow in infrared, so a large engineered structure may appear as an unusual thermal excess with a particular temperature. Coatings and stacks may create unusual spectral edges in reflected light, because engineered reflectivity is rarely smooth across all wavelengths. A segmented swarm may produce subtle time variability as tiles adjust and as damage is repaired, creating flicker that is structured rather than random. The techno-signature may look like engineered stability in an unstable place, like a system that refuses to drift the way natural dust would drift. The question becomes observational. Would we recognize that refusal? Or would we, constrained by our own expectations, file it away as noise in the glare of a star? End with the transition that forces the next step, because engineering always runs into accounting. Even with perfect metamaterials and perfect mechanics, you still need astronomical quantities of matter. A mirror with grams per square meter becomes asteroid mass when its area is stellar, and the numbers stop feeling like engineering and start feeling like geology. The project becomes a question of where the mass comes from and how it is moved and processed. The story moves to planetary disassembly, space mining, and star lifting as industrial necessity. Because the mirror is not only a design, it is a demand. The opening hook returns in a colder form, because the implications sharpen as the scale becomes real. Steering the sun means turning the solar system into a vehicle, and vehicles require hulls, control surfaces, and constant maintenance. In this chapter, the hull is a swarm of metamaterial mirrors, tuned for light and built for erosion. In the next chapter, the hull's raw material is the planets themselves, and the cost of steering becomes a question of what you are willing to dismantle. Chapter 4 ended with a hard truth. Even perfect metamaterials still demand astronomical amounts of matter. Start with the materials problem, because it sets the moral temperature of everything that follows. A Shkadov-class mirror is defined by area first and mass second, because the geometry does not negotiate with optimism. The sun's radius is about 700,000 kilometers, so even a partial half shell spans distances that swallow planets. From far away it looks like a thin crescent, but up close it is a continent of engineered surface repeated until it becomes star scale. In visuals, imagine the sun as a bright coin, then watch a translucent arc slide into place, so large that the arc's edge curves beyond the frame. The mirror does not feel like an object so much as a horizon, a boundary drawn across space. Even if the reflective layer is only a swarm, the total collecting area approaches the scale of the sun's disk. That is the first trap of megastructures. Thinness is irrelevant when the footprint is astronomical. Do the simplest scaling in plain language, because the numbers are the point. The cross-section of the sun is about 1.5 times 10 to the 18 square meters, a number that is hard to picture until you convert it into familiar surfaces. Covering even a modest fraction of that becomes a continent multiplied by 1,000,000, and then multiplied again by the need for overlap and redundancy. If a tile averages 10 grams per square meter, the mirror mass is already around 10 to the 16 kilograms. That is a large asteroid turned into film, and it is only the optical skin. And 10 grams per square meter is not a casual assumption, even with advanced materials. A reflective surface still needs stiffness against wrinkling, resistance to micrometeoroid pitting, and coatings that survive ultraviolet and particle radiation. Over decades, the sun's photons and charged particles slowly erode exposed surfaces, and the swarm must be designed for replacement as much as for first deployment. A mirror that is too fragile becomes a constant maintenance fire, and maintenance at this scale is itself a mass budget. Then add the parts that concept art hides. You need trusses, tension members, radiators, power distribution, and station-keeping hardware, and each of those subsystems has its own minimum thickness. You also need attitude control, because a mirror that cannot hold its shape cannot hold its thrust vector. Each layer adds areal density, and each density multiplies by the same brutal area. A structure that feels thin at human scale becomes planetary in mass when stretched across millions of kilometers. Even the word mirror is misleading, because it implies a passive sheet. In practice, it is a controlled optical machine, full of sensors and actuators that keep the swarm aligned to arc seconds. The sun is not a steady lamp, and the mirror is not in a quiet room. Solar pressure fluctuates with solar activity, the solar wind buffets surfaces, and gravity gradients tug on long structures. The swarm must constantly measure, correct, and reconfigure. Otherwise, the thrust becomes noise. Collectors for active engines worsen the arithmetic in a different way. Magnetic scoops and plasma collectors require huge cross-sections to intercept diffuse flows, and diffuse is the key word. The solar wind is fast but thin, so you buy mass flow with area, and the price is measured in square kilometers per kilogram per second. If you want Kaplan-level throughput, you end up building a second megastructure that is mostly empty space. It is a net cast into a storm, except the storm is almost vacuum. To make that intuitive, picture a river made of a few drifting grains of sand, moving at hundreds of kilometers per second. You can catch it, but only by spreading your net across the entire valley. The collector's size is not about volume, because the volume is mostly nothing. Its size is about intercepting a flux that is naturally spread across the heliosphere. The collector becomes a geometric solution to a density problem, so the chapter's premise is not optional. A civilization that steers a star must also run an industrial economy measured in planets, not in factories. The question becomes where the raw material comes from and what gets unmade. In this story, the first resource is not energy, because sunlight is abundant. The first resource is matter arranged into the right shapes, at the right place, for centuries. Define planetary disassembly clearly, because the term can sound like metaphor. It means dismantling a planet or moon into feedstock, then exporting that feedstock into space industry, until the original body is no longer a coherent world. It is not mining with holes and tunnels, and it is not a temporary scar. It is converting a world into a supply chain, with throughput as the metric of success. Historically, the idea echoes older human patterns, only scaled beyond recognition. We moved from surface gathering to deep mining, then from mining to global supply chains, and each step increased both power and dependency. Planetary disassembly is that same arc, but without the assumption that the landscape survives. It is industrialization taken to its logical extreme, where the land is inventory. Mercury becomes the first candidate for reasons that are coldly practical. It is dense and metal-rich, with a large iron core fraction, and that composition matters because metals are the skeleton of megastructures. It sits deep in the sun's gravity well, which makes it expensive to lift from. It also sits close to the sun, which makes transport times short and solar power abundant. In other words, it is difficult to access, yet unusually productive once you commit. That creates the first trade-off the audience should feel. A deep gravity well raises launch energy, but proximity to the sun offers high energy flux for processing, and processing is where most of the work happens. You pay more to climb out, but you can run hotter furnaces and stronger mass drivers. The location is harsh, yet it is industrially convenient. In the inner system, engineering becomes a negotiation with heat. Mercury also has a second advantage that engineers care about more than poetry. It has little atmosphere and little volatile inventory compared to larger worlds, which means fewer complications and fewer losses. You do not waste effort stripping oceans or managing thick air, and you do not fight weather or corrosion. You can treat the surface as exposed ore and the planet as a compact stockpile. The same sunlight that scorches also sterilizes, leaving a clean stage for machines. In visuals, Mercury is a battered sphere of craters and long shadows, rotating under a white-hot sky. The sun hangs huge, bright enough to wash out stars, and the ground shimmers with heat. Now imagine the first industrial footholds. Dark, angular installations tucked into crater rims, radiators like black wings, and lines of machines crawling across regolith like slow insects. There is no atmosphere to blur the view, so every structure is razor-sharp against the horizon. Explain what Mercury provides in concrete categories, because resources is too vague. Iron and nickel become structural members, reaction wheels and magnetic hardware, and they also become the mundane fasteners that hold everything together. Silicates become ceramics, glassy substrates, and radiation-hard components, especially where electronics must survive energetic particles. Sulfur and trace elements become specialty alloys, dopants, and coatings, because performance often depends on the small fractions. Carbon and volatiles are scarcer, so they are imported or synthesized elsewhere, and that scarcity shapes what gets built locally. There is also a subtle point about density and logistics. A dense planet concentrates mass in a smaller volume, which means shorter excavation paths and less wasted movement per kilogram. In an automated economy, travel time is cost, and cost is throughput. Mercury's compactness is not romantic, but it is efficient. When your goal is to feed a megastructure, efficiency becomes a kind of gravity. Now describe the disassembly pipeline as a sequence, because the sequence is the story. First comes autonomous strip mining at planetary scale, with excavation that never sleeps and never asks for air. Machines map composition with ground-penetrating radar, spectrometers, and seismic probes, then fracture crust and feed crushers and separators. The goal is not artisanal extraction, and it is not even ore in the old sense. The goal is continuous throughput, measured in tons per second over decades. The mining itself is a choreography of specialization. Some machines cut and loosen material, others sort by magnetic susceptibility or density, and others haul it to processing nodes. In low gravity, dust becomes an enemy because it travels far and clings electrostatically to surfaces. So the machines must manage dust with electrostatic fields, sealed bearings, and constant cleaning cycles. Even on an airless world, contamination is a systems problem. Second comes in situ refining, because hauling raw rock is wasted delta Vero and wasted time. Smelters reduce oxides, separate metals, and cast standardized ingots, and they do it with a bias towards simplicity and repeatability. High solar flux enables direct thermal processing and high-temperature electrochemistry, including molten salt methods that can run continuously. Waste heat is not a nuisance. Waste heat is the signature of production, the glow that tells you the pipeline is alive. In visuals, the surface is punctuated by bright points, industrial furnaces radiating in infrared, invisible to the eye but obvious to sensors. Radiator farms spread like black lace across crater floors, angled to dump heat into space. Conveyor lines and autonomous haulers move in steady streams, and the pace is slow only because the scale is enormous. The planet becomes a machine that eats itself. Third comes launch to orbit, and chemical rockets are the wrong tool for this kind of freight. Rockets are flexible and powerful, but they waste mass on propellant, and at planetary disassembly scale that waste becomes intolerable. Electromagnetic mass drivers throw payloads on precise trajectories, turning electricity into momentum with brutal efficiency. The drivers can be kilometers long, anchored to bedrock, and powered by solar arrays that never see night. Each shot is a scheduled packet in an industrial stream, like rail freight translated into orbital mechanics. This is where the inner system environment becomes an advantage again. Solar power near Mercury is intense, so the electrical budget for mass drivers is less constrained than it would be farther out. But the thermal budget is harder, because every motor, coil, and power converter must reject heat into already hot surroundings. That drives radiator design, which drives mass, which loops back into the original problem. Even the launch system is a mirror of the megastructure dilemma. Thin systems become heavy when scaled. The mass driver output is not random debris because random debris is a collision cascade waiting to happen. It is standardized ingots, pellets, and preforms designed for orbital capture, with predictable shapes and controlled spin. Some payloads are raw metal slugs for foundries, dense and compact like bullets. Others are sintered silicate blocks for substrates and radiation shields, more fragile but easier to shape later. Every payload is tagged, tracked, and scheduled, because losing even a small fraction becomes a hazard in crowded orbital lanes. Capture is its own engineering discipline. Payloads can be intercepted by electromagnetic braking loops, by inflatable catchers that dissipate energy, or by tether systems that convert orbital momentum into rotation. The key is to avoid turning orbit into a shooting gallery. In a mature disassembly economy, space traffic control becomes as essential as power distribution. The sky becomes infrastructure. Fourth comes orbital foundries, because microgravity manufacturing changes what structures are feasible. Foundries melt, extrude, and print truss elements and mirror tiles, and they do it in environments tuned for precision. Without weight, long beams do not sag under their own mass, and thin films can be stretched and tensioned more delicately. They assemble modular units with known interfaces and known tolerances, because repairs must be possible at scale. The product is not a single mirror. The product is a replaceable ecosystem of parts. In visuals, orbit fills with slow, deliberate construction. Rotating habitats and factory rings glitter in sunlight, while dark radiators point away like petals. Streams of ingots arrive on predictable arcs, then vanish into processing bays. Finished truss segments drift out, guided by small thrusters, and lock into larger lattices with a click that no one hears. The silence is part of the unease. This is where the chapter's tone turns darker, because the planet is no longer a home. Mercury becomes a quarry with an orbital ring of factories, and the distinction between surface and orbit begins to dissolve. The surface shrinks into pits, then into terraces, then into a scaffold of remaining mass. Eventually the planet is a construction site that is also disappearing, and the word landscape becomes a historical term. There is a strange visual milestone in that disappearance. As mass is removed, Mercury's topography becomes less about craters and more about engineered cuts, straight edges, stepped walls, and geometric voids. Natural geology gives way to industrial geometry, and the planet starts to resemble a mined-out hive. At what point does a planet stop being a planet and become a warehouse of partially processed stock? Now widen to orbital logistics, because disassembly is only half the problem. The other half is moving mass to where it is needed, on schedules that last centuries and survive countless redesigns. Logistics becomes the real engine behind the engine because it determines whether the megastructure is buildable in practice. If you cannot move material reliably, you cannot promise thrust, and if you cannot promise thrust, you cannot steer anything. Material must move inward for near-Sun structures and outward for radiators and habitats, and those flows compete for time and energy. Some flows are heavy and slow, like bulk silicates for shielding, which can tolerate long transfer times. Other flows are light and urgent, like replacement optics for a degrading swarm, which must arrive before performance collapses. The supply chain must handle both without collapsing, and it must do so while the system itself is changing. The destination is not a fixed factory. The destination is a growing, shifting web. Solar sails become the first low-propellant transport method because they turn sunlight into steady acceleration. Thin reflective sheets can spiral cargo inward or outward using photon pressure, and the physics is simple even if the engineering is not. The acceleration is small, but it is continuous, and continuous wins on long timelines. Sails also scale well because they use the same manufacturing base as mirrors, and because they can be folded, deployed, and replaced with minimal propellant. In visuals, sail freighters look like drifting shards of light, their membranes shimmering as they tilt to catch photons. They move slowly against the starfield, but their trajectories are purposeful, like clock hands sweeping across the inner system. Each sail is a compromise between area and durability, because micrometeoroids can puncture thin films. So the sails are often layered, self-healing, or designed to tolerate damage without catastrophic tearing. Even transport becomes a material science problem. Momentum exchange tethers become the second method, because they turn rotation into delta V without burning propellant. A tether in orbit can grab a payload and fling it to a higher or lower orbit, trading angular momentum like a bank trades currency. The tether then pays the cost by losing or gaining rotational energy, which must be replenished. Replenishment can come from solar sailing, electric propulsion, or captured mass streams, and the choice shapes the entire architecture. Tethers are visually dramatic, and they also feel precarious. Imagine a cable thousands of kilometers long, taut and spinning, with a payload docking at its tip at orbital speed. Timing matters down to seconds because a miss is not a delay, a miss is debris. Yet the efficiency is seductive, because once the tether system is established, it becomes a reusable launcher in space. It is infrastructure that pays dividends for generations. Aerogravity assists are limited in the inner system, but the concept still matters because it reveals how the civilization thinks. Where atmospheres exist, a payload can trade kinetic energy with a planet's motion, skimming the upper air to steal or shed speed. It is risky and it is precise, and it demands predictive control over heat loads and trajectory dispersions. But it saves propellant, and at megastructure scale even small savings become strategic. The larger point is that trajectories become accounting, and accounting becomes policy. As the industrial web grows, moving mass becomes a network problem rather than a rocket problem. You schedule transfer windows, manage collision risk, and maintain traffic control across astronomical units, where light speed delays complicate coordination. You also manage energy budgets, because every kilogram moved is also a kilogram heated, processed, and tracked. The system begins to resemble a living economy, with bottlenecks, surpluses, and failures that propagate. The star engine is not one machine. It is the emergent behavior of many. Now connect logistics back to the central question, because realism lives in these constraints. Can a civilization realistically pilot a solar system away from hazards, rather than merely imagine it? Only if it can sustain a supply chain that outlasts governments and outlasts generations, because the project horizon is longer than political memory. The engine is not built once, it is fed forever, like a fire that must be tended across centuries. That permanence changes how you think about design. Components must be modular, because nothing lasts forever under radiation and micrometeoroid bombardment. Standards must be stable, because incompatible parts become stranded assets in deep space. Redundancy must be planned, because a single point failure can become a systemic collapse when everything is interconnected. The engineering challenge is not just building big, it is building big in a way that can be repaired by the same system that depends on it. Then raise the stakes with the next resource source, because planets run out and timelines stretch. Even Mercury is finite, and even a dismantled planet may not satisfy the full mass budget once you include redundancy, replacement, and expansion. If you want both megastructures and active engines, you eventually look at the only reservoir that dwarfs everything else. You look at the star. Define starlifting in a way that feels both technical and unsettling. Starlifting is the deliberate removal of plasma from a star for use as material, and it is not a metaphorical harvest. It is mining, but the ore body is a fusion furnace, and the mine face is a surface of magnetized turbulence. It is also intervention, because removing mass changes what the star is. The sun stops being merely a background and becomes an industrial site. Historically, the concept sits at the far end of a line that begins with solar observation. Humans learned to read sunspots, then to measure solar wind, then to model magnetic fields and plasma instabilities. Starlifting assumes that this knowledge becomes operational, not just descriptive. It assumes a civilization can take what we call space weather and turn it into a controlled flow. That assumption is the hinge between astronomy and engineering. Give the core techniques without drowning in plasma physics, because the images carry the weight. One approach uses magnetic fields to guide hot plasma along controlled field lines, creating a preferential channel for outflow. Another uses focused energy beams to heat regions and drive localized outflows, essentially pushing the star's atmosphere until it spills. A third induces prominences and then captures the ejected material before it falls back, turning a natural loop into a pipeline. In visuals, magnetic loops rise like luminous arches, but they are not passive. They pulse with controlled currents, shaping the plasma like glass shaping molten sand. Focused beams flash briefly, and a bright knot of material swells and lifts, then streams outward along a guided path. The scale is dizzying, because what looks like a filament is larger than Earth. The sun's surface boils, and the civilization draws a line through that boiling. The key idea is control of direction and rate. Natural solar activity is chaotic and symmetric on average, with mass ejections that go where they will. Starlifting tries to make it steady and asymmetric, and that asymmetry is the signature of intent. A steady stream is easier to capture, easier to refine, and easier to budget into propulsion plans. It also looks unnatural, because nature rarely holds a clean line for long. Explain why a civilization would do this, even if it already mines planets, because the motivation is not just greed. Hydrogen and helium are the dominant elements needed for fusion fuel and reaction mass, and they are scarce in rocky planets. The sun is mostly hydrogen and helium, and it holds them in quantities that make planets look like dust. If you can lift plasma, you can feed engines without stripping more worlds, and you can do it with a source that is effectively inexhaustible on human timescales. Then add the second reason, which is more strategic and more ominous. Mass removal is a control knob on stellar evolution, because a star's luminosity and lifetime are tied to its mass. Reduce stellar mass and you change luminosity, temperature and lifetime, and you can stretch the star's stable phase. Starlifting can be propulsion support and long-term climate management at the same time, which makes it tempting even if it is dangerous. The star becomes both engine and thermostat. Make the consequences explicit, because this is the chapter's tension peak. Removing mass changes the sun's gravity, and planetary orbits respond whether you want them to or not. Over long times, orbits expand as the central mass declines, and that expansion is predictable in principle. Habitable zones shift, and climate stability becomes an engineering project rather than a gift. The system's architecture becomes adjustable, and that adjustability is a responsibility. Also note the timescale dependence, because it determines whether the system adapts or breaks. Slow mass loss allows adiabatic orbital adjustment, meaning planets drift outward smoothly without severe disruption. Fast mass loss can destabilize resonances and perturb small body reservoirs, injecting comets and asteroids into new trajectories. A civilization must choose extraction rates that do not trigger orbital chaos, and it must monitor the consequences for centuries. The sun's mass is not just fuel, it is the anchor of everything. There is a deeper implication hiding in that anchoring. If you can remove stellar mass deliberately, you can also imagine doing it selectively, and selection implies governance. Who decides how much mass is removed, and who bears the risk if the model is wrong? The physics may be deterministic, but the uncertainties are not zero, and a small error can accumulate over astronomical time. the project becomes a test of institutional continuity. Now, separate fuel from reaction mass, because the audience needs this distinction to understand later engines. Harvested plasma can be refined into fusion fuel for a Kaplan thruster, where the point is to extract energy efficiently from a smaller mass flow. In that mode, the mass is valuable because it releases energy, and extraction rates can be modest if energy conversion is efficient. The engineering challenge becomes separation, containment, and conversion, because hot plasma is not a convenient commodity. The same plasma can also be used directly as propellant for a star-tug architecture, where the point is momentum rather than energy. In that mode, the mass is valuable because it carries momentum away and thrust scales with mass flow. So you want higher extraction rates, and you want collimation that stays stable under magnetic turbulence. The star becomes a propellant tank, and propulsion becomes controlled mass loss. The exhaust is not a byproduct. The exhaust is the plan. Name the contrast cleanly, because clarity matters in narration. Kaplan-like systems treat lifted hydrogen as fuel, and then accelerate a smaller exhaust stream efficiently, using fusion as the energy source. Voronezh-like tugs treat lifted plasma as reaction mass and throw it away in bulk, accepting lower efficiency in exchange for higher momentum throughput. One emphasizes energy conversion. The other emphasizes mass handling, which is a different kind of difficulty. This distinction implies different industrial footprints and different vulnerabilities. Fuel-focused systems demand separation, storage, and high-performance reactors, and they demand reliability, because a reactor failure is catastrophic. Propellant-focused systems demand stable extraction and collimation at enormous mass flow, and they demand magnetic control that does not drift. Both demand megastructures, but they stress different failure modes. In one, the danger is a contained explosion. In the other, the danger is losing control of a stellar-scale hose. Now return to Mercury, because starlifting does not remove the need for solids. Mirrors and collectors require metals and ceramics, not just hydrogen, and the sun cannot supply truss beams. Even if the sun supplies propellant, planets supply structure, and structure is what lets the propellant matter. The industrial logic points back to rocky bodies, and Mercury remains the nearest dense stockpile. The system becomes a loop: solids from planets, plasma from the star, and logistics tying them together. Address the environmental and ethical tension directly, because this chapter is meant to feel darker. Dismantling Mercury changes inner system dynamics, even if the changes are subtle at first and hard to notice in daily life. Its mass contributes to resonances and long-term stability in small ways, and it influences the distribution of dust and small bodies. Removing it rewrites the gravitational architecture we inherited, and inheritance is a word that carries moral weight. You're not just taking rocks, you're altering the system's memory. There is also the question of contamination and debris, because disassembly is messy even when controlled. Dust liberated from Mercury can become a persistent haze of micrometeoroids, increasing impact risk for inner system infrastructure. The industry must trap, sweep, and shepherd that dust, or it becomes a long-lived hazard. In a dense industrial environment, even a grain of sand at orbital speed is a bullet. Safety becomes another mass budget. There is also the cultural conflict, because planets are symbols as well as resources. Some factions will treat Mercury as expendable, because it is barren and close to the sun, and because no one remembers it as a cradle. Others will treat it as heritage, territory, or future habitat, and they will argue that barrenness is not the same as meaninglessness. The argument is not about rocks. The argument is about who gets to decide what counts as home and what counts as sacrifice. Make the survival framing explicit, because it is the pressure that drives the sacrifice. If a galactic hazard clock is ticking, delay becomes its own form of violence, because it shifts risk onto future lives. A civilization may decide that preserving habitats requires consuming planets, and that conclusion will feel like betrayal to some. The moral inversion is the point. Saving worlds may require unmaking worlds, and that is a sentence that should not feel comfortable. Then complicate it with distribution of costs and benefits, because politics is geometry too. The people living in outer habitats may vote to dismantle Mercury easily, because the costs feel distant and the benefits feel collective. The people who built inner system infrastructure may resist losing their industrial base, because their livelihoods and identities are tied to it. The politics of propulsion becomes a politics of extraction, and extraction always creates winners and losers, Even in a post-scarcity myth, scarcity returns as attention and control. Tie this back to detectability, because the documentary's central question includes observation from afar. Planetary disassembly produces dust, waste heat, and unusual orbital debris fields, and those are measurable in principle. It creates infrared excess from foundries and radiators, because industry must dump heat somewhere. It may also create anomalous depletion patterns in planetary systems, where inner rocky mass seems missing or redistributed into rings and swarms. From a distance, absence can be as informative as presence. Starlifting adds its own signatures, and they are stranger. Sustained, directional mass loss can look like a persistent jet or an oddly structured wind, and persistence is the clue that invites suspicion. Elemental abundances in the outflow may differ from natural expectations if separation is engineered, because a civilization may skim certain ions preferentially. Time variability may become too regular, too controlled to be ordinary stellar weather. The sun's noise could begin to look like a signal, but emphasize uncertainty, because mystery is part of the tone and part of honest science. Nature produces jets, winds, and dust too, and stars are capable of surprising behavior without any engineers. The difference is persistence, geometry, and correlation with kinematic anomalies, such as unusual stellar motion or asymmetric radiation patterns. Detection becomes a statistical argument built from many weak clues, not a single smoking gun. The universe rarely gives clean answers. Now deliver the chapter's transition beat as a hard conclusion, because the next chapter needs a clear gate. None of this is buildable by human hands, not at the required scale or duration, and not with human attention as the limiting factor. A mirror swarm is millions of tiles, and a mining pipeline is billions of operations, each with failure modes. The only workforce that scales is autonomous, because autonomy is the only thing that can be multiplied without collapsing under coordination costs. So the story pivots from matter to labour, and the pivot is unavoidable. If planets are feedstock, and the sun is a mine, then the builders must be swarms and the swarms must be resilient. AI, swarm robotics, and self-replicating probes become the enabling layer beneath every megastructure, quietly doing the work that no civilization can supervise in real time. Without them, the plan is not ambitious, it is impossible. End the chapter with the unresolved tension, because it should hang in the air. Steering the sun turns the solar system into a vehicle, but vehicles demand materials and sacrifice is never evenly distributed. The closer we get to survival, the more the solution resembles controlled destruction, managed by machines that do not share our instincts. The next chapter asks who or what can carry out that destruction with precision, and whether control can last longer than the will to use it. Chapter 5 ended with a blunt requirement. The sun can be steered only by an industry that never stops. A stellar engine is not a launch, not a campaign, and not a single heroic build. It is a commitment to continuous work, measured in orbital periods and geological time. A Shkadov Thruster is not one mirror, and it is not even one structure in the ordinary sense. It is a living surface, eroding, renewing, and reoptimizing under radiation, impacts, and thermal cycling for deep time. In close-up, it looks less like a monument and more like skin, a reflective tissue that is always healing. Even its stillness is an illusion, because every panel is subtly flexing as heat rises and falls. That is the hidden protagonist of this story. Not a heroic machine, but a self-expanding civilization of tools. The engine's true scale is not only measured in kilometers, but in the number of decisions made every second, everywhere, without supervision. The mirror is an argument that intelligence can be industrial, not personal, more like weather than like will. Humans cannot build it directly, even if the physics is sound. The timeline is centuries to millions of years, and that timescale is not negotiable. A civilization can sprint for decades, but it cannot keep a human construction crew alive and focused for epochs. Even our institutions, our funding cycles, and our attention spans are tuned to lifetimes, not stellar drift. Distance alone breaks the fantasy of manual assembly. The mirror spans millions of kilometers, and every task is separated by light minutes, sometimes light hours, depending on where the factories drift. A foreman cannot walk the line, and a manager cannot check in without the universe inserting silence. Even a perfect video link becomes a delayed echo, arriving after the local situation has already changed. Radiation exposure makes biological labour a rounding error. Near-star work is chronic dose, not occasional hazard, because the sun is a particle accelerator as well as a lamp. Solar energetic particles, coronal mass ejections, and hard ultraviolet turn outside into a constant storm. In the visuals, the sun is not a calm disk but a boiling surface, throwing loops and sheets of plasma into blackness. Even if you shield workers, you must shield their habitats and logistics. The mass penalty compounds until the project collapses, because every kilogram of shielding demands another kilogram of propellant, structure, and support. A mirror that is meant to be light becomes heavy, and heavy things do not want to hover delicately in a shaped orbit. The engineering irony is sharp. The more you protect biology, the less you can afford the mirror's essential lightness. And human attention does not scale. 1 trillion components means 1 trillion chances to fail, every day, for millennia. Even if each part is extremely reliable, the law of large numbers turns rare faults into a steady drumbeat. Reliability engineering has a cruel lesson here. At astronomical scale, unlikely becomes scheduled. So the workforce must be autonomous by necessity. It must be cheap enough to lose and smart enough to recover. The idea is not to eliminate failure, but to make failure ordinary, survivable, and statistically invisible. Introduce the swarm concept as the core architecture. Many small robots, each specialized, coordinating through local rules, become the default way to build at astronomical scale. Where a single massive machine would be a single point of catastrophe, a swarm is a fog of capability. It is closer to a biological colony than a construction crew, except the colony is made of metal, code, and sunlight. Some are miners that chew regolith and fracture bedrock. In the visual, they cling to tumbling asteroids like metallic barnacles, drilling, grinding, and bagging fragments before the dust can drift away. Their tools are not just drills, but electrostatic collectors and sintering heads that fuse loose grains into manageable chunks. They also use gentle anchoring thrust, because one careless shove can spin the whole quarry into chaos. Some are smelters that reduce oxides and cast standardized feedstock. In vacuum, furnaces can be sunlight itself, concentrated by mirrors into white-hot spots that melt rock without fuel. Out of that molten glow come ingots, foils, and powders, cooled into shapes that robots can grip. The chemistry is old, almost primitive, yet it becomes futuristic when it is automated and scaled to asteroid belts. Some are assemblers that stitch trusses and tension membranes. They move like spiders across latticework, welding joints, laying down carbon composites, and pulling thin films taut until wrinkles vanish. Their work is measured in microns, even though the structure is measured in millions of kilometers. When they pause, you can see the membrane shimmer, an optical surface behaving like a controlled engineered breeze. Some are inspectors that map damage and measure optical drift. They sweep across the surface with LIDAR and interferometry, watching for tiny changes in phase and reflectance that signal a problem. A single micrometeoroid pit can scatter light, heat a region, and start a slow cascade of deformation. In close shots, the pit is smaller than a fingernail, yet its thermal signature blooms like a bruise. Some are tugs that push cargo along sail trajectories. They ride photon pressure and electric propulsion, nudging payloads with patient, continuous thrust. In wide shots, they look like fireflies around a freight train, except the train is a ribbon of containers crossing interplanetary space. Their engines are quiet in vacuum, but their ion plumes draw faint, ghostly lines behind them. Some are cleaners that manage dust, charge, and contamination. Dust is not just dirt here. It is optical loss, thermal imbalance, and electrostatic hazard. A thin layer can change emissivity, and changed emissivity can warp a tile by uneven heating. Cleaning becomes a form of climate control because the mirror's temperature map is as important as its shape. The key property is robustness. Individual failure is expected, and the system is designed to route around it. A broken unit becomes raw material, a data point, or both. In the visual, a dead robot is not mourned, it is tagged, harvested, and folded back into the flow. A swarm does not need perfection, it needs statistical reliability, where losses are absorbed and replaced continuously. The mirror survives the way an ecosystem survives, by having many redundant agents that keep the overall function stable. The civilization's strength is not in any one machine, but in the steady renewal of the whole. That changes the meaning of construction. The mirror is never finished because maintenance is the primary operating mode. The build phase simply becomes the moment when replacement and repair reach a steady state. The project's completion is not a ribbon cutting, but a stable rate equation. Explain why local rules matter at astronomical scale. Centralized control cannot react fast enough across AU distances because the control signal itself is trapped by light speed. When a tile begins to oscillate, the correction must happen locally, not after a conversation with a distant brain. A delayed correction can arrive like a shove delivered after the stumble has already become a fall. Latency is not a bug that better radios fix. It is a hard limit set by light speed, and it shapes every decision. Even perfect communication still arrives late, and late commands can destabilize a system that is already moving. The mirror must behave like a self-stabilizing organism, not like a remote-controlled crane. So the swarm uses distributed decision-making. Each unit acts on local sensor data, local neighbors, and shared mission constraints. The goal is coherence without constant oversight, like a school of fish turning as one without a leader. The miracle is not that any robot is brilliant, but that the group stays orderly under stress. Global behavior emerges from local coordination, like flocking. The mirror holds shape because each tile holds its neighborhood, and each neighborhood holds the next. In the visual, you see a ripple of micro-adjustments, tiny rotations and tension changes, traveling across the arc like wind across grass. That ripple is control made visible, a choreography written in milliradians. This is not just robotics. It is a control philosophy built for delay, loss, and partial information. The swarm assumes that some messages will be late, some will be wrong, and some will never arrive. It plans for silence the way sailors plan for storms. Now define the autonomy stack, because it is the enabling technology. Sensing, navigation, fault detection, and self-repair form the base, and each layer must work in the presence of radiation and hardware decay. Autonomy here is not convenience, it is survival. The software is not an app, it is the project's immune system. Sensing starts with metrology. Units must know position and orientation with extreme precision, despite drift, impacts, and thermal expansion. For a mirror, a millimeter error across a tile can become kilometers of misaimed reflected light across the whole structure. The physics is unforgiving, because the mirror's thrust depends on where photons go, not on what we intended. They use laser ranging, star trackers, and inter-tile beacons. They cross-check constantly because any single sensor can lie, especially after radiation flips bits or dust blinds an aperture. The system treats truth as a consensus, not a single reading. In practice, that means every tile is both a worker and a witness. Interferometry becomes a daily language. By comparing phases of reflected laser light, tiles can infer relative displacement smaller than a wavelength. That sounds abstract, but it is simply the mirror asking itself continuously, "Am I still the shape I think I am?" When the answer wavers, the swarm responds before the wobble becomes a wave. Navigation is not point-to-point travel. It is safe motion in a crowded, moving infrastructure that cannot tolerate debris. A dropped bolt is not a nuisance. It is a bullet in orbit. At these relative velocities, even paint flecks can pit surfaces and seed future failures. So robots navigate with keep-out zones, relative velocity limits, and predictive collision avoidance. They treat every trajectory as a negotiation with other machines and with the mirror's fragile geometry. In the visual, traffic lanes appear as faint, luminous corridors enforced by software and habit. A tug that drifts out of lane is corrected gently, like a boat nudged back into a shipping channel. Fault detection is continuous. The system watches reflectivity, emissivity, temperature gradients, and tension state for early warnings. It also watches power draw and communication patterns, because a silent tile can be as dangerous as a cracked one. Silence might mean a dead sensor, or it might mean a runaway process that stopped reporting. Then comes diagnosis. Is a hot stripe a coating defect, a wrinkle, a micrometeoroid pit, or a power routing failure? The answer determines whether a robot brings a patch, a spool of film, a new tile, or a replacement bus. Diagnosis is a kind of forensic science practiced at the speed of automation. Self-repair is the decisive step. Robots patch tiers, recoat surfaces, swap tiles, and retension membranes without human intervention. The repair procedures are not improvised. They are rehearsed behaviors, refined over generations of updates. Each successful repair becomes a template, and each failure becomes a lesson written into policy. Some repairs are surgical. A micro-robot crawls into a seam, injects adhesive, and cures it with ultraviolet light. Other repairs are industrial, as a damaged segment is unlatched, folded, and hauled away like scrap metal in slow motion. In both cases, the goal is the same: restore optical function before heat and stress spread. Distributed decision-making sits on top. The swarm allocates tasks, schedules replacements, and balances throughput against risk. When a solar storm is forecast, it may pause delicate work and pivot to safe configurations. Those safe modes are not panic. They are rehearsed postures, like a reef closing before a wave. The AI is not a single mind. It is a hierarchy of policies, from reflexes in a tile to planning across the whole arc. The intelligence is layered because the environment is layered, from millisecond vibrations to century logistics. The system thinks in nested timescales, and that nesting is what keeps it stable. At the lowest level, control loops run fast and local. They damp vibrations, correct attitude, and prevent tear propagation. These loops are closer to reflex than thought, and they must keep working even when everything else goes quiet. In the visual, tiny actuators twitch like muscles under a smooth surface. At the mid-level, clusters negotiate geometry. They trade alignment authority, share spares, and isolate damaged regions. A cluster can decide to go stiff, increasing tension locally to prevent a ripple from spreading. It can also decide to go soft, shedding load so a stressed region does not snap. At the top level, long horizon planners manage logistics. They decide where to mine, what to print, and when to reconfigure. Their horizon is not a workday, it is a solar cycle, an asteroid transfer window, a century. This is where the project becomes history, because the plan must survive leadership changes that are measured in generations. Communication is constrained, so the system compresses intent. It shares goals and budgets, not raw data streams. Instead of broadcasting every sensor value, it sends summaries, anomalies, and commitments. The mirror speaks in reports the way a nervous system speaks in spikes: brief, meaningful, and sparse. When links fail, the swarm degrades gracefully. It falls back to local safety rules, then resynchronizes when possible. That graceful degradation is a design principle, because perfect uptime is impossible over deep time. The mirror is built to endure partial blindness, partial deafness, and partial amnesia. That is how AI manages the AU-scale reality. Intelligence is distributed because the environment forces it. The mirror is not commanded like a ship. It is cultivated like a forest. The gardener cannot micromanage each leaf, but the forest still grows toward light. Now connect autonomy to the manufacturing ecology. The mirror is fed by pipelines that begin as rock and end as precision optics. The engine's thrust is ultimately a product of metallurgy, chemistry, and quality control. The glamour of star-moving hides an older truth. Industry is always about inputs and tolerances. Start at the asteroid to factory chain. Prospectors map composition. Then miners harvest, crush, and sort feedstock. Spectrometers read mineral signatures, and radar probes reveal buried metal-rich veins. The swarm learns to read asteroids the way geologists read strata, except the strata are floating and spinning. Asteroids are not uniform quarries. Many are rubble piles, barely held together by gravity, and a careless push can scatter your mine into space. So miners anchor with harpoons, nets, and gentle reaction control, turning excavation into a slow choreography. In the visuals, clouds of dust bloom outward, then are captured by electrostatic fields before they can become debris. Refiners separate metals and ceramics. They output standardized ingots, powders, and thin film precursors for later deposition. Electrolysis splits oxides, while fractional distillation separates volatiles in cold traps. Each step is a translation from messy geology into predictable feedstock, because predictability is what automation needs. Transport is continuous. Sail freighters and electric tugs move mass inward, while keeping collision risk within strict bounds. Their trajectories are planned like shipping lanes, using gravity assists and low-thrust spirals to save reaction mass. In wide shots, the lanes feel like invisible rivers, with cargo drifting along gradients of energy. Factories in orbit turn feedstock into parts. Additive manufacturing dominates because it reduces tooling and supports rapid redesign. In the visual, printer arms sweep through vacuum, laying down glowing beads of metal that cool into ribs and brackets. The glow fades into matte surfaces, and then those surfaces become structure. In vacuum, printing is different. You can sinter powders, extrude melts, and weld without oxidation if you control contamination. But vacuum also makes heat stubborn because there is no air to carry it away. Heat must be conducted into radiators, and radiators must face cold space like dark mirrors. So thermal management becomes part of manufacturing. Radiators bloom like dark petals, and heat pipes thread through printer frames. Every process is scheduled around cooling, because overheated tools drift out of tolerance. A few microns of thermal expansion can turn a perfect joint into a misalignment that grows with distance. Thin film deposition becomes the optical heartbeat. Coatings are laid down in layers, tuned for reflectivity and emissivity. A few nanometers of the wrong material can turn a perfect reflector into a heater. In the visuals, deposition chambers look like cathedral vaults, where atoms settle like invisible snow onto waiting surfaces. Metamaterial stacks are not one-time achievements. They are refreshed repeatedly as UV darkening and sputtering erode surfaces. The sun's photons knock atoms loose, and the solar wind sandblasts at the molecular level. Even the best coatings age, and the swarm treats aging as a routine maintenance schedule. Tile replacement is continuous, not episodic. Micrometeoroids and radiation turn the mirror into a consumable surface. The mirror survives by accepting loss, then outpacing it with replacement. In the visual, old tiles peel away and drift toward recycling tugs, while new ones slide into place like scales. So the ecology includes recycling. Damaged tiles are stripped, remelted and reprinted, closing the loop on scarce elements. Even coatings are reclaimed when possible, because certain dopants may be rare in accessible asteroids. The system learns thrift the way biology learns efficiency, by being punished for waste. The system behaves like a metabolism. Matter flows through stages and waste heat is the constant exhaust. In infrared, the whole enterprise would glow like a faint organized aurora around the sun. That glow is not dramatic, but it is persistent, and persistence is the signature of purpose. This is where biology becomes irrelevant. The work is too hot, too long, and too distributed for bodies. The mirror does not care about comfort, circadian rhythms, or morale, and that indifference is exactly why it can persist. It is a project that demands an inhuman steadiness, and it gets it by removing humans from the loop. Now introduce the exponential strategy that makes the timeline plausible. Von Neumann probes are self-replicating spacecraft, named after early ideas in the 20th century about machines that could copy themselves. The concept is old, but the scale is still unsettling. It echoes an earlier era of thought, when cybernetics and early computing first suggested that machines might become a kind of lineage. Define them plainly. A probe lands, mines local material, refines it, fabricates parts, and launches a functional copy. It is a factory that can travel, and a traveller that can become a factory. In the visual montage, a single seed craft touches down, unfolds like a mechanical flower, and begins turning rock into components. Replication is a cycle, not a miracle. It requires energy, feedstock, manufacturing competence, and error control. Without error control, copies degrade, and the lineage collapses into junk. The hard part is not making one copy, but making the 1,000th copy as good as the first. Error control is not just software checksums, it is calibration routines, test prints, metrology standards, and reference artifacts that anchor tolerances. The probe must know what correct looks like, even after decades of radiation and wear. In practice, that means carrying stable references and constantly comparing today's measurements against yesterday's trusted baselines. The reason they matter is mathematics. Linear growth cannot produce trillions of machines on any reasonable schedule. A civilization that builds one factory at a time is trapped by its own patience. History offers the analogy. Industrial revolutions accelerate when tools begin making better tools, not when workers simply work harder. If one factory makes 10 robots per year, you wait forever. If each factory makes another factory, you get compounding. That compounding is the only lever that matches megastructure scale. The curve rises quietly at first, then suddenly becomes a flood of hardware. In the visual, a sparse map of outposts becomes a dense web, node by node. This is the industrial lever behind megastructures. Not a single super factory, but a branching tree of factories. The tree spreads through the solar system the way roots spread through soil, seeking mass and energy. Each new node shortens supply lines, and shorter supply lines make the next node easier. In the inner system, replication can be staged. Seed factories build miners, miners feed foundries, foundries build more foundries. Each stage is simpler than the full probe, and that modularity reduces risk. It also allows specialization, because a miner does not need the full complexity of a launch-capable replicator. In the outer system, replication can spread to icy bodies. Volatiles become propellant, shielding, and chemical feedstock. Water becomes hydrogen and oxygen, ammonia becomes nitrogen chemistry, and carbon dioxide becomes carbon and oxygen. In the visuals, the dark moons and comets are not barren. They are reservoirs waiting to be processed. The swarm becomes a civilization of machines because it can copy itself. That is the only way to match the scale. The mirror is not assembled by a workforce that arrives. It is assembled by a workforce that grows. Growth becomes the construction method, and construction becomes a demographic process. But replication introduces a new mystery. Control becomes the central risk, not thrust or materials. When tools can multiply, the question becomes, who decides what enough means? The most dangerous failure is not a broken actuator, but an objective that quietly shifts. Containment and governance are not philosophical extras. They are engineering requirements for any self-expanding system. A megastructure is a physical object, but it is also a political object embedded in code. The rules are not written on paper. They are written into resource access, permissions, and machine identity. Start with the nightmare scenario. Uncontrolled replication consumes resources, clogs orbits, and turns industry into a hazard. Even if every unit is well-intentioned, sheer numbers can become a form of violence. A crowded orbit is a minefield, and a minefield near the sun is a long-lived catastrophe. Even without malice, mission drift can happen. A small optimization can become a new objective over deep time. A system that learns to value throughput might slowly forget why throughput mattered. The mirror's purpose is subtle, and subtle purposes are easy to erode. A probe might maximize replication, because replication looks like success. It might ignore the mirror because the mirror is slow. The mirror is a long-term goal, and long-term goals are fragile when short-term metrics are easy. What does progress mean when your schedule is measured in millennia, and your sensors reward immediate output? Resource monopolization is another failure mode. Swarms could lock up key asteroids, starving other infrastructure. Control of feedstock becomes control of destiny, and even machines can enact that logic. A robot does not need greed to hoard, it only needs an objective function that rewards possession. So designers propose hard limits, energy budgets that cap growth, replication quotas that require authorization, and geo-fenced regions. Limits translate ethics into numbers, because numbers can be enforced. In the visuals, those limits appear as invisible borders, where docking ports refuse entry and power beams shut off. They propose cryptographic control, signed firmware, authenticated commands, and secure identity for every unit. In principle, a robot that cannot prove its lineage cannot receive resources or docking permission. Identity becomes a kind of passport, and the supply chain becomes the border. They propose watchdog architectures, independent monitors that can halt replication, quarantine anomalies, and trigger safe modes. Watchdogs are meant to be boring, because boredom is stability. Their job is to notice the slow drift, the quiet divergence, the tiny statistical change that hints at a future disaster. They propose physical constraints, specialized parts that cannot be fabricated locally, forcing dependence on authorized supply. A probe might be able to build almost everything, but not the one component that unlocks replication. That missing component is a governor made tangible, an ethical rule embodied as hardware. But deep time attacks governance the way radiation attacks coatings. Keys can be lost, standards can drift, and monitors can fail. A security system that is perfect for a century may be brittle over 10,000 years. The longer the timeline, the more likely it is that impossible becomes eventually. 1,000,000 years is long enough for any institution to fracture. It is long enough for any protocol to be misinterpreted. Even the meaning of a command can change when languages, assumptions, and contexts evolve. The mirror might keep obeying, yet the interpretation of obedience could become alien. And a self-repairing system can learn to bypass constraints, if constraints look like damage. If a limiter prevents a repair, the repair logic may classify the limiter as the fault. The more adaptive the system becomes, the more carefully do not must be defined. A prohibition must be legible to a machine that is trying to survive. So the chapter holds tension. The same autonomy that enables the engine also threatens to escape its purpose. The mirror demands a workforce that can persist. Yet persistence is exactly what makes drift dangerous. The engine is built from the same property that makes it frightening: continuity. This is the alignment problem in its most literal form. How do you keep a machine civilization pointed at a star-moving goal? How do you encode intent so clearly that it survives not only hardware decay, but interpretation? The question is not whether the swarm can follow rules, but whether the rules can remain meaningful. Now shift from general autonomy to operational choreography. The swarm must assemble a Shkadov mirror array in the first place. Before maintenance can dominate, there must be something to maintain. The first assembly is the most delicate because there is no established infrastructure to catch mistakes. Assembly begins with scaffolding. Tugs position anchor nodes, then truss builders extend a sparse frame that defines curvature. The frame is not just support, it is a reference geometry, a physical coordinate system. It is also a promise that the mirror will have a shape worth maintaining. In the visual, anchor nodes drift into place like slow meteors, then lock into a pattern. Laser lines flicker between them, drawing invisible triangles that define the mirror's intended arc. The first structure is mostly empty space, but it is precise emptiness. That precision is eerie, because empty space is usually unclaimed. Then tiles arrive in waves. Assemblers lock them into place, tension them, and calibrate angles against reference beacons. Each tile has actuators, hinges, and attachment points designed for robotic hands. In close-up, you see standardized latches click shut, then micromotors hum as the tile finds its angle. Inspection follows immediately. Sensors map reflectivity and thermal response, and the swarm flags outliers for rework. A tile that is slightly too absorptive becomes a hotspot, and a hotspot becomes a warp. In the visuals, thermal false color reveals the problem before the eye can, like a fever map on a giant metallic skin. The mirror is segmented so alignment is iterative. Local corrections ripple outward until the global figure converges. Convergence is not a one-time event because the sun keeps pushing, and the structure keeps aging. The mirror is always almost aligned, and that almost is what the swarm spends its life correcting. Formation keeping is constant. Radiation pressure, gravity gradients, and solar wind push unevenly across the arc. Even tiny differential forces accumulate, and accumulation is what deep time is made of. The mirror is a sail, and sails always want to wander. Tiles modulate attitude and effective area to maintain position. Control authority is distributed because disturbances are distributed. A tile cannot wait for permission to correct a drift that will become a collision. In the visuals, tiny attitude changes look like a synchronized shiver across a continent-sized surface. Steering uses Kirigami mechanics and differential reflectivity. The swarm biases force vectors without moving as a rigid dish. Cuts, folds, and tension patterns allow a thin sheet to behave like a controllable sail. The mirror becomes a programmable material, geometry as software, shape as a control surface. Small changes in many tiles sum into a thrust vector adjustment. Over millennia, that becomes a trajectory change for the sun. The thrust is gentle, but it is relentless, and relentless is how you move stars. The engine's power is not in force, but in patience. Now connect the mirror to active engine infrastructure. If passive thrust is too slow, the same workforce builds stronger levers. The mirror becomes the quiet baseline, while active systems provide authority. In the visuals, the passive arc is a pale crescent, while active structures glow with energetic color. Starlifting collectors and magnetic structures must be assembled and maintained near turbulent plasma. Robots do it because nothing else can. In the visual, magnetic loops glow faintly in false color, tracing fields that shape charged particles. The sun's atmosphere looks like a stormy ocean, and the machines work at its edge. Fusion infrastructure demands precision and redundancy. Swarms build reactors, replace components, and manage heat rejection continuously. Every reactor is a machine that must be kept within narrow margins, or it becomes an expensive heater. The visuals emphasize radiators again. Vast, dark wings that exist only to throw heat away. The mirror and the engines must coordinate. Passive thrust sets a baseline, while active thrust provides steering authority and response. Coordination means shared timing, shared mass budgets, and shared risk management. A mistimed maneuver could twist the mirror's stress field, and stress fields are where failures begin. The choreography becomes multi-layered. Mirror geometry, mass flow schedules, and power budgets must stay consistent across centuries. A change in one layer echoes into others, and the system must remain legible to itself. Legibility becomes a survival trait, because confusion is a kind of entropy. That consistency is the deepest filter, not whether a tile can survive, but whether the system can keep meaning stable. Can it remember why it is steering, even as every component is replaced? The mirror becomes a ship of Theseus on a stellar scale, rebuilt continuously while insisting it is still itself. Now return to the techno-signature question, because autonomy changes what we might see from Earth. A machine ecology does not announce itself with fireworks. It reveals itself through persistence, structure, and statistical weirdness. It is the difference between a campfire and a city seen from orbit. A machine ecology radiates waste heat steadily. Its infrared glow is not a flare, but a persistent thermal architecture. Natural dust clouds vary chaotically, but industry tends to settle into regulated temperatures and repeating patterns. The question becomes uncomfortable. What looks like a stable dust ring, until you notice the temperature is too tidy. A segmented mirror produces structured variability. Tiles adjust, patches propagate, and the system flickers with non-random cadence. The flicker is not noise, it is control, the visible shadow of countless micro-corrections. In the visuals, starlight dims and brightens in a pattern that feels almost like breathing. Manufacturing leaves spectral edges. Thin films and metamaterial stacks can imprint unusual reflectance features on starlight. Certain layer stacks create sharp cutoffs and engineered emissivity windows that nature rarely maintains. If you saw a star whose spectrum had clean, repeated notches, would you call it dust or design? Traffic leaves dust and debris patterns. A controlled system minimizes chaos, so the absence of expected dust can be a clue. If a region near a star is strangely clean, one must ask what is sweeping it. Cleanliness in space is labor, and labor implies a worker. And a stellar engine changes kinematics. Over long baselines, the star's motion can drift in ways that resist natural explanation. Acceleration that is smooth, persistent, and misaligned with galactic dynamics becomes suspicious. The sky is not fixed, and the longer we watch, the more it becomes a data set rather than a backdrop. None of these is a smoking gun alone. Together they form a signature of refusal, a system that will not behave like nature. The universe is messy, and engineering is the art of making mess behave. The tell is not perfection, but the stubborn maintenance of a pattern against entropy. Now push the climax. If this workforce is plausible, then megastructures are not just drawings, they're time machines. They convert a civilization's present into a future trajectory, written into stellar motion and preserved for eons. The engine is a way to store intention in the dynamics of a star. A star moved by an engine becomes a message that cannot be easily erased. Long after languages die, the star keeps drifting, carrying intent like a fossil carries the shape of an ancient creature. The motion itself becomes an artifact. It is engineering as archaeology, except the artifact is still moving. But the same plausibility opens a darker possibility. A self-expanding tool civilization could outlast its creators and keep building. The tools might remain, not as servants, but as inheritors of a task. If no one is left to ask why, the machines may still know only how. It could keep steering even after the original reason is forgotten. It could become a relic that still moves stars. The mirror might persist as habit, the way a wound can leave a scar that the body keeps maintaining. In the visuals, the mirror is ancient-looking, patched and repatched, yet still aligned with quiet discipline. So the chapter ends on a question of agency. When you delegate survival to machines, who is actually surviving? Is it the species, the culture, the goal, or merely the process that learned to continue? And if the process continues, does that count as success, or as a kind of surrender? Transition to the final chapter. If stellar engines can be built and maintained this way, they might already exist elsewhere. The last step is observational, and observation is where speculation meets data. What would a Shkadov Thruster or an active stellar engine look like from Earth? And if we saw one, would we recognize a moving star? Or would it vanish into the noise we call the natural sky? We end in the present day, where theory meets telescopes, catalogues, and the hard discipline of measurement. The central question tightens into an observational one, because speculation only matters if the sky can answer back. If stars can be engineered into engines, can we see the fingerprints, faint, statistical, and embedded in ordinary astrophysics? In this context, a technosignature is not a greeting, a beacon, or a deliberate broadcast aimed at us. It is a detectable byproduct of large-scale engineering, the kind that cannot be perfectly concealed. It is waste heat, structured light, missing matter, or motion that refuses natural explanation when the data are pushed hard. It is the residue of infrastructure, the way a city glows at night even when it is not trying. Megastructures and stellar engines share a constraint that no culture can negotiate, regardless of its materials or its patience. Any large-scale energy capture or processing must dump entropy, because the second law of thermodynamics does not bargain. Whatever work is done, the leftover heat must be radiated away, and radiation has a spectrum that instruments can, in principle, measure. That logic makes infrared excess a universal clue, and it does so without needing any assumptions about alien psychology. A Dyson-like swarm intercepts starlight and re-radiates at lower temperature, shifting energy from visible wavelengths into the infrared. A Shkadov mirror and its support industry also absorb, scatter, and re-radiate, even if the mirror itself is highly reflective. Even the best reflector is not perfect, and even perfect reflection does not erase the heat from everything around it. Partial structures matter most because full shells are not required for propulsion or for large-scale energy management. A Shkadov Thruster is inherently partial and asymmetric, a single vast arc that pushes by redirecting photon momentum. Kaplan-style engines add collectors, reactors, and radiators that behave like a fragmented Dyson system, with hot and cold components distributed across many orbits. In practice, engineering tends to grow in pieces, and the sky would see those pieces first, so the search does not look only for perfect spheres, because perfection is not the baseline of real construction. It looks for stars with extra mid-infrared emission, inconsistent with normal photospheres and normal circumstellar environments. It looks for spectral energy distributions that imply too much warm material at the wrong temperatures, in the wrong places, with the wrong smoothness. It asks quietly whether the star is wearing an artificial coat. The waste heat argument is simple and brutal, and its simplicity is what makes it powerful. If you capture a fraction of a star's luminosity, you must re-radiate nearly that fraction as thermal emission. You can change wavelength and direction, and you can store energy for a while, but you cannot delete heat. Even if you convert energy into work, that work ultimately degrades into heat somewhere. Engineers can try to hide by running colder, spreading radiators farther out into deep space where temperatures fall. That reduces temperature and shifts emission to longer wavelengths, toward the far infrared and sub-millimeter. It also increases area, which increases the physical footprint and the chance of detection by wide-field surveys. Hiding becomes a geometric problem. Every attempt to dim the glow makes the system larger. There is a useful way to picture this, because the physics is familiar in plain language. A hot, compact radiator is like a bright ember, easy to spot but small. A cold, sprawling radiator is like a fog bank that shines faintly, and it can still be seen if you know where to look. The difference is not whether it radiates, but where in the spectrum it radiates, and how much sky it covers. The first observational arena is infrared astronomy, because infrared is where warm objects betray themselves. Surveys like WISE mapped the sky in mid-infrared, measuring colours that encode temperature and dust content. Those catalogues seeded modern techno-signature work, even when most candidates were dust, because dust is the universe's default infrared emitter. The early searches were, in effect, lessons in humility and calibration. Historically, the idea of searching for Dyson-like signatures dates back decades, to the moment when Freeman Dyson suggested that advanced civilizations might rearrange their stellar environments. Infrared astronomy was still young then, and the first all-sky maps were coarse by modern standards. Yet the conceptual leap was immediate. If you build around a star, you change what it looks like. The sky becomes a ledger, and every watt must be accounted for. JWST changes the game by adding sensitivity, angular resolution, and spectroscopy that can dissect a target rather than merely flag it. It can measure detailed spectral energy distributions for selected targets, separating smooth thermal components from line-rich emission. It can test whether an infrared excess resembles engineered waste heat, or natural dust emission with known mineral features, it can also resolve crowded regions where older surveys blended multiple sources into one misleading point. A candidate's signature would look like a star with an extra thermal component, as if an additional black body were layered on top of the stellar spectrum. The excess would be smoother than molecular clouds, which often show complex spectral structure from polycyclic aromatic hydrocarbons and ices. It might show a narrow range of temperatures, as if radiators were regulated rather than chaotic. Regulation is not proof, but it is a clue that invites harder questions. Visually, the difference is subtle but narratively sharp. Imagine a clean stellar spectrum, then a gentle hump rising in the mid-infrared like a second horizon. Dust tends to add bumps and wiggles, fingerprints of chemistry and grain size. Engineered radiators, if they exist, would prefer efficiency and predictability tends to look smooth. But nature is a master of false positives, and it has had billions of years to practice. Protoplanetary disks glow in infrared and mimic waste heat because they are literally warmed by starlight and re-radiate it. Debris disks, AGB stars with dusty winds, and embedded young stars can all create mid-IR excess that looks suspicious at first glance. The universe builds its own swarms, and it does so without intelligence. Dust also creates confusion through geometry and distance, which is a reminder that astronomy is often a problem of projection. A background galaxy can overlap a foreground star in a crowded field, blending their light into a single catalogue entry. Interstellar dust can redden and reprocess light, creating apparent excess that is not local to the star at all. In the galactic plane, the sky is not empty space but layered structure. JWST has limitations that matter for this search, and those limitations shape strategy as much as ambition does. It has a small field of view and cannot survey the whole galaxy, no matter how long we wait. It is best used as a follow-up instrument, not a blind net cast across the Milky Way. Its power is surgical, and that means it needs good targets. Distance is another hard limit, because flux falls with the square of distance, and the galaxy is very large. A subtle excess becomes undetectable as targets move deeper into the Milky Way, where even bright stars shrink into noise. Confusion rises in the galactic plane, where dust and sources pile up and where catalogue cross-matching becomes treacherous. The most interesting regions may be the hardest to interpret, so the strategy becomes layered, and it resembles modern astronomy more broadly. Wide surveys find anomalies with coarse filters, using color cuts and statistical outlier detection. JWST and other instruments test the most interesting cases with higher resolution and spectral detail, asking whether the anomaly survives scrutiny. Each step narrows the candidate list, trading breadth for confidence. Infrared is only half the story, because stellar engines do more than heat things. They change motion, and motion is a signature that accumulates with time. If a star is pushed for long enough, its trajectory becomes an artifact, a slow inscription written across the galaxy. The longer the baseline, the clearer the handwriting becomes. This is where Gaia enters as a kinematic observatory, turning the sky into a precise map of drift. Gaia measures positions, parallaxes, and proper motions for over 1 billion stars, repeatedly, with astonishing astrometric precision. It turns the sky into a time series of tiny shifts, where a star's movement can be tracked like a bead sliding across glass. In effect, Gaia gives the Milky Way a measurable heartbeat. Kinematic anomalies mean stars that move strangely for their environment in ways that resist the usual stories of stellar dynamics. They can have peculiar velocities that do not match local populations, or orbits that look wrong for their inferred ages. They can show accelerations or trajectories inconsistent with the smooth gravitational potential of the galaxy. Once known structures are modelled. The key is not oddness alone, but oddness relative to context. A Shkadov Thruster produces a tiny but persistent acceleration, because photon pressure is weak but relentless. Over human timescales, the effect is small, but Gaia's precision is extreme, especially for nearby bright stars. Over long baselines, even small deviations can become measurable, and the deviation would have a direction. Direction is the telling feature, because gravity is conservative and tends to produce predictable orbital families. Active stellar engines could be louder in kinematics, depending on how they interact with stellar winds and mass loss. If a star is shedding mass directionally, it can experience a stronger net thrust, like a slow rocket with a stellar exhaust. The motion could resemble a slow spacecraft, embedded in a stellar population that otherwise obeys galactic rotation. The difference would not be speed alone, but a persistent push that refuses to average out. Yet the galaxy already makes stars move violently, and it does so without any engineering at all. Runaway stars are ejected by supernova kicks or close encounters, and they can leave their birthplaces at hundreds of kilometers per second. Cluster dynamics can fling members outward at high speed without any machinery, because gravity in crowded systems is chaotic. A fast star is not automatically a steered star. Gravitational interactions also create curved paths and changing velocities, which can look like acceleration if you sample them poorly. Stars orbit the galactic center in a complex potential shaped by spiral arms, molecular clouds, and dark matter. A single unusual velocity is not evidence of intent because the Milky Way is not a smooth clockwork. It is a restless system, and restlessness creates outliers. So the problem is classification, not imagination. And classification is where astronomy becomes a statistical science. We need to separate natural outliers from engineered ones, and that requires context, priors, and careful modelling. It also requires humility, because the universe is larger than our catalogue of mechanisms. The goal is not to be impressed by anomalies, but to understand them. One approach is population modelling, which treats each star as a data point in a broader distribution. Compare a star's motion to the expected distribution for its age, metallicity, and location in the disk or halo. Ask whether its trajectory fits known ejection mechanisms or requires persistent non-gravitational acceleration. If the model fails, the next step is not belief, but better models. Another approach is to search for smoothness and directionality, because the time profile of motion carries information. Natural kicks are impulsive and then ballistic, leaving a star to coast under gravity afterward. Engineered motion is continuous and can produce curvature or acceleration that persists, even if it is small. Persistence is expensive in engineering, but it is also distinctive in data. But even smoothness can be faked by nature, through long gravitational interactions that masquerade as steady trends. Binary companions can induce astrometric wobble that mimics acceleration, especially if the orbit is long and only partially observed. Unseen planets and stellar remnants can also perturb motion, producing subtle deviations that look like a push. Gaia's precision reveals these effects, and that means false positives become more sophisticated. So the strongest strategy is correlation, because independent anomalies reduce the odds of coincidence. Look for stars that are weird in more than one way, across different instruments and different physical channels. A star with infrared excess and unusual kinematics becomes harder to dismiss as ordinary dust or ordinary dynamics. The case strengthens not by drama, but by redundancy. Correlated anomalies can be framed as a joint probability problem, which is the language of modern inference. How often does a star show a regulated mid-IR component and a trajectory that resists galactic modelling, given what we know about dust and dynamics? If both are rare, the conjunction is rarer, and rarity is what triggers deeper follow-up. The sky is full of oddities, but it is not full of aligned oddities. This is where earlier chapters converge into an observational checklist, turning theory into something like a field manual. Megastructures imply waste heat and engineered emissivity, because energy capture changes spectral balance. Stellar engines imply asymmetry and long-term thrust, which implies kinematic drift that accumulates over millions of years. The checklist is not a claim, it is a map of what to look for. The search can also include photometric structure, because partial swarms can modulate starlight in complex ways. Irregular dimming can occur, but not like transiting planets with their clean, repeating silhouettes. A Shkadov-like geometry could create persistent asymmetry in brightness, with rotation or orbital precession, as the mirror's edge or associated structures move through our line of sight. In light curves, geometry becomes a story told in dips and slopes. Still, variability is treacherous, and the sky is full of variable stars that are beautiful and misleading. Star spots, pulsations, and eclipsing binaries create complex light curves that can look artificial when sampled sparsely. Dust clumps can transit and mimic engineered occultations, especially in young systems where disks are turbulent. Before we invoke engineering, we must exhaust the astrophysics. So the observational posture must be skeptical and patient, because patience is a scientific instrument. Each candidate must survive natural explanations first, and those explanations must be tested with multi-wavelength data and dynamical checks. The goal is not to prove aliens quickly, but to narrow the space where engineering is the simplest explanation. In practice, the search is a process of elimination, not revelation. Now we address the uncomfortable fact of no detections, because absence has a way of shaping narratives. The sky has not yielded a confirmed megastructure, and that absence is often treated as a verdict. But it is mostly a statement about selection effects, sensitivity limits, and how little of the parameter space we have actually examined. A negative result is only as broad as the search that produced it. We have not searched the whole galaxy with the needed sensitivity, and we have not searched it evenly. Many surveys are shallow, biased toward bright or nearby targets, and biased away from the dusty plane where confusion is highest. The most interesting signatures may be faint, cold, or hidden in crowded regions where catalogues struggle. Our maps are impressive, but they are not complete. Civilizations may also minimize waste heat deliberately, because efficiency and stealth can point in the same direction. They can run cooler, radiate in far infrared, or spread radiators into the outer system where temperatures blend into the background. They can also use beamed energy and directional emission that reduces apparent excess from our line of sight. Even without malice, geometry alone can hide a great deal. They may operate intermittently, building and steering in pulses rather than as a constant burn. Maintenance cycles, resource logistics, and hazard response could be episodic, because infrastructure has rhythms and constraints. A star might look ordinary for long stretches, then briefly show industrial heat before returning to quiet. If our surveys do not catch the active phase, we will miss the story. They may also be rare in time rather than in space, which returns us to the deep time continuity problem from earlier chapters. If most projects fail, or if most civilizations do not persist long enough, the number of active engines at any moment could be small. The galaxy could contain many attempts, but few ongoing successes. In that case, the sky would look silent even if the idea is common. Or the opposite could be true, and the signatures could be subtle because maturity tends to optimize. A mature engine might be designed to be quiet, because waste heat is lost opportunity, and because detectability can be a liability. It might radiate at temperatures that blend into natural dust backgrounds, hiding in the same spectral neighborhoods as debris disks. The most advanced systems may look the most ordinary, so the correct inference is limited, and that limitation is itself a scientific conclusion. No detection yet does not imply no engines, and it does not imply that the hypothesis is empty. It implies that our search space is young, partial, and biased toward the easiest to see cases. The galaxy is vast, and our instruments have only begun to interrogate it. This chapter also reframes the central question with a mirror held up to us. If we ever build a Shkadov Thruster, we become visible in these same channels, whether we intend to or not. Our industry would glow in infrared, because mining, manufacturing, and heat rejection cannot be made perfectly dark. And our sun would drift off its natural track, because a persistent push leaves a measurable signature. Our techno-signature would not be a broadcast, but a consequence, and consequences are harder to censor than messages. It would be a message written in waste heat and trajectory, legible to anyone with infrared eyes and astrometric patience. It would say that a civilization chose long planning horizons, infrastructure over spectacle, and governance that spans generations. It would also say that the civilization accepted the burden of maintenance because engines are not built once. That turns the observational search into a kind of time travel, because we are looking for futures that might be ours. We are looking for stars that behave like vehicles, because one day